All right, I'll get started. Prepping for a thunderstorm as we go. So Julia is here, and if my video goes out, it's probably unlikely. That's what it's about. All right, so there were two questions during the interim. One was about the difference between, let's say, fit resamples and tuning. So the question is, if I want to skip tuning parameters after doing my resampling splits, can you just use the same code as we did for the easy eval from the other session? So no, the fit resamples function that we used yesterday just for resampling is when your model is specified completely. So like if you knew the number of neighbors, or like for this model, if you had a value of penalty you were happy with in the mixture between ridge regression and lasso, then you could use that fit resamples and then just resample that model. But if you don't, if you need to do tuning, you don't have to use grid search. We'll talk about a sequential search in a little bit, but you'd have to use some sort of tuning algorithm to finalize what those values are. So the previous stuff we did yesterday before we started this regression session is more about when you have a completely specified recipe and model where you know all the tuning parameters, then you could use fit resamples to evaluate that. So I think that's the answer to that question. Can I comment on finalized workflow and finalized recipe? So you'll see them more as we go. Those finalized functions for models and recipes and workflows are when you have some final parameters that you like, then you can sort of like splice them back into their original objects. So for example, when we create this linear regression object here, we don't know what penalty and tune are. So once we have values that we like for those finalized functions will take the values that you give them and put them in place of these tune values. So you'll see that. We'll talk about Mars next. You'll see finalized workflow in action for that, where it replaces the unknown parameters for a recipe and the model at the same time. So you'll see that in a little bit more. Another question is about dynamic panel data using group vfold CV. And I want to do a rolling window resampling. Do I nest the data frame first, and how? So I'm assuming, so when we did the survey, there was somebody who put in some comments about having maybe group data and how to resample that. And I'm thinking maybe this is the same person. So it would help to know more. But so let's say you have like patients or people, let's say, over time. And let me know if that's the question or not if you're here. And so in those instances, what we would want to do is, well, we think about like what the independent experimental unit is. So when you think about like the Ames data, the independent experimental unit is the house. So when we resample that, since there's only one row per house, we don't have to really do anything special, because when we resample at the level of the independent experimental unit. But let's say we have people in our data set and we have followed them over time. Well, within a person, there is correlation between their data. So like if you were in part of like a medical trial, let's say for, I don't know, something related to like metabolism. I'm not a runner. So for example, like if you had somebody run on a treadmill, the data that you would get on me over time, within my data points are correlated to each other because they're all related to me. And those would be independent of like somebody else who's like a runner who got on a treadmill and got their data. So within my data, that data is correlated, and within that other person's data, that data is correlated. But me and that other person are independent of each other. So you have like you almost have like a hierarchical structure where where some data is correlated with each other and some data is not. So typically what we would do is we would use that group K-fold, group V-fold cross-validation to sample data at the person level. And so when it does its splits of which data go into training or testing and so on, what it would do is it would take, let's say I'm a person who goes into the training set, then it would take all the rows associated with me to the training set together. It wouldn't take some of my data and put it in training and some of it in assessment. So all my data would come over as a block. So that's kind of like a block resampling. So unless I'm understanding the data incorrectly, I don't think you would do any rolling window resampling, probably. At least I don't think so, because all of your data would come along at the same time. So when you resample, you would resample at the person level. So the talk I'm giving on Saturday morning, or I think it's like noon, has an example of data in a clinical trial where we like leave one patient out. So let's say if we have like 50 patients, one way to do this would be to take all of one patient's data, hold it out as the assessment set, fit your model on 49 patients and predict the one that was held out, and then do that round robin. So I'll show an example of that. The other thing I would point you towards is we talk about this a little bit in the feature engineering book. So we have a chapter with some examples. We call it profile data, but that would be probably a place I would suggest to look. And if your data is more complicated than I'm getting, then definitely post something else with some more details, and I could comment on it in Slack as we go. I'm going to wait a second because there's a little more typing. Speaking of hierarchical data, does Parsnip support multi-level engines such as LME4? Yes. So there's a package that's not on CRAN yet. So if you go to the tidymodels repository, this is what I'm talking about on Saturday. There's a package called, what did I call it? Multi-level. I can't remember what I called it. Multi-level mod. And what this does is it gives you, it adds some additional engines to Parsnip for building hierarchical models using STAN or LME. So, so this part's all working. It's what I'm going to demonstrate on Saturday during my talk. The resampling works fine. I'll show you on Saturday. There's some API changes we want to make to workflows that make it a little bit easier to specify those models with tidymodels. So it all works, and I'll show you a running example. Actually, might already have. I'm trying to figure out if I've already put up the slides or not. Let me see. Talk. I'll make this repo public probably Saturday, but in there I have an R Markdown file that shows how you would build like a LME model for repeated measures data. Yeah. So if you want to test it out, that's great. It's not on CRAN yet, so you can install it from GitHub, and I'm still working on it, but it's working enough to present. So if there's anything lacking in there or any features you see that would be helpful, it'd be great to put in issues on that. Does tidymodel support model averaging? Of what type? So there's a lot of ways you could do that. There's like Bayesian model averaging, there's bagging, and like ensemble methods. So a little more specificity would help answer that. If you're looking for averaging over models, we have a package for bagging called Baguette. And that has bagging methods for the models we typically would use bagging for. That's an ensemble metric or ensemble model. Bagging is that would take like multiple models from slightly different data sets, make a bunch of individual models, and then when you go to make a prediction, you average out the predictions from the individual models. And we're going to talk about boosting a little bit later, so that's a similar method. So yeah, so we do have some things, but there are like a variety of ways that you can fit those models. So there's, again, different ways of doing that. So let us know if there's something that we should have mentioned. Let me also post this in the notes. Okay, any other questions? Okay, well, if you have them, put them in there and I will answer them. Here's where we left off, was we were talking about the glibnet model with this regularization tool, and we used some time series resampling methods and fit a variety of models. I just talked about parallel processing and showed you how to run that model in parallel. And so then what we could do is, so we got through like running this, and then what we would at this point would do is we would kind of examine the resampling profiles versus the tuning parameters and see what values seem to be good and which ones weren't for these tuning parameters. So one thing we can do is, if you just want to get them and like do some dplyr stuff, you can do that. So if we take that tuning object we just created and run collect metrics on it, that gives us a tibble back with RMSE and R squared for all of the tuning parameter combinations, which I think we tested like, I think 50, maybe 100 models. So that would be 100 by 2, or 100, we have 200 rows, 100 models, and then 2 metrics. And then you can filter out, for example, if you just want RMSE values. The other thing you can do, which works quite nicely, is we have an auto plot method for these tune objects. And since this is a regular grid, since we did a cross product of mixture and penalty values, it makes a plot that looks like this. So you can see on the top panel here, we have RMSE, and bottom panel's R squared. We want to minimize RMSE, so we can look at these different profiles. Now, the red one here is a almost completely ridge regression model, and that tends to have, especially when the amount of regularization gets smaller, it tends to have, you know, a little bit suboptimal performance. But then anything that has like a sizable proportion of lasso to it seems to have smaller RMSE values. And you can see, you know, I talked about yesterday about performance plateaus, where there are some tuning parameters that have sort of a constant level of performance across their range. And this is a good example. It seems like for this model, it does not want a ton of regularization. As the amount of regularization goes up, so does the RMSE, which is bad. So it seems to me like anything from about this value to the lowest value would probably give you effectively the same sample size, both across those penalty ranges, but also across the amount of mixture. So, you know, you could pretty much choose whatever you wanted to. There's one that's numerically best, but, you know, they're not really all that different. So if it were me, I would probably look at maybe, what we'll do in a minute is select the best, but one thing I would consider doing is using the model that has 100% lasso, because that's going to select the most features out of the model. So that's going to do the most elimination. And then find a value that's maybe not so close to where it increases here, maybe around here, to pick as a tuning parameter value. So, you know, sometimes you can eyeball these things and you can look at what the optimal, like numerically optimal is, but then you might want to, for other reasons, adjust that parameter finalization. A number of people have asked to have tidymodels just automatically select the best and do a bunch of other stuff based on that, and I'm very resistant to doing that. Carrot does that, and I kind of wish I hadn't, because it lets us sort of unconsciously just go with the flow and do whatever the machine tells us, and I don't necessarily think that's a great idea. So you can look at these plots and look and see, you know, what grabs you in terms of the best parameters. We also have a function called show best, where if you don't give it a metric, it'll pick one and sort by them. But what this will do is it will give you the top 5 models based on the metric. So it sorts them by the lowest RMSE, because it knows RMSE should be small. And you can see that the values it likes the most in the top 5 have a high degree of lasso regularization and relatively small values. So 0.003 would be like right in here somewhere. We might be able to add a little more regularization by coming to the right a little bit, but it's not going to, I don't think, substantially change things. So, the one that's numerically best is this one right here, 75% lasso and a penalty of 0.003. The mean or the RMSE for that combination, again, this is in thousands of people, is 1.16. And you can see they're all within a certain numerical tolerance, the same within that range. So you could choose any of these if you want. We'll just use the select best, which will take the best one just for simplicity, and save that. And as I showed, I think I showed this previously, that produces a tibble that has the parameter values that are correspond to the best thing. There's other things you can do, like select by the one standard error rule and some other tools. So you don't have to select a numerically best one. There's other, you can look yourself and choose, but there's other selection functions in tidymodels. So at this point, we've run our tuning grid. We have all the resampling results. We've picked one that we think is, probably good enough for the GlimNet model. And so one thing we also probably want to do, so I can look and say, well, the RMSE is 1.16. I think that's pretty good, but it doesn't actually, it's hard to say kind of like, well, how well did that work? So a professor of mine once said the only way to be comfortable with your data is not to look at it. And I think I mentioned that on the first class. So one thing we can do is, you may remember when we set the options here, we use this save pred equal true and use that as the control value. And so that will save all the assessment set predictions. So these are predictions of data points that were not used in the model fitting. And so much like collect metrics, we have another function that can collect the predictions, which is unsurprisingly called collect predictions. And when we run that, it gives us a tibble back. Now the tibble is quite large, it's 22,000 data points. And the reason for that is it has all the holdout data sets across all the time slices, but it also has it for all 100 models. So you can see like, here's a model and here's a model. So for the same row here of the original data, we have 100 rows corresponding to all the tuning parameters. So we probably want to maybe plot the data based on the ones that we think are best. So we just selected the best penalty and mixture value. And then we have the data across all the penalties and mixtures. So we can do an inner join between those two things to get the data we want to keep. So if I take those collected predictions and just filter on them by joining on the optimal penalty values, I can just do a simple ggplot against observed and predicted. That goes quite a long way to understanding performance. One little bit here that's inside Tune is we have our own coordinate method where what it does is it gets the total range of the observed and predicted values, plots the plot in a square so that the axes have exactly the same scales. So that's what that does. And you can see the result here where for the holdout predictions during the week, those look pretty good. They're not perfect. They could be tighter around this green line, which is the best possible situation. But, it's not bad. Then you have, the weekend data. It's not bad either, but you see it's falling off the line, even though it's linear, where what it's doing is in cases where it's actually 5, it's predicting it to be a little bit less than 5. So it's sort of under predicting on the low end a little bit. And then we have some data points, this is a substantial outlier and this is. So, especially with these data, it's a great teaching example because you start to wonder like, okay, what is it about these data points that make them difficult to predict? And so you end up doing a lot of detective work where you might go back and look and see, was there something about this date that is special that I could maybe add another predictor for? So, the first time we sort of naively ran these analyses, we found all these outliers. And once we looked at them, they were all the holidays. We were like, oh yeah, duh, we should put holiday predictors in there. So what we would do is we would look at these and do something similar. Why are they outliers? Why are they big residuals? And is there anything we can do about it? So let's take this one here. we predicted ridership to be, I don't know, like 10.5 thousand people, but in actuality, it was more like 6 maybe. So what we can do is we can take the predictions for this model. We can compute the residuals, the observed versus predicted. We can sort of sort them by their largest residuals, and then just plot the worst 4 offenders. So this data frame has the 4 largest residuals, but we kind of want to figure out what data that's from. So what we can do is we can either bind them back with the original data, look and let's say what the date is, or like we could look at the weather. So there are some data in this range that we fit the model, where there was like a blizzard where the L trains just shut down in the mornings. So there are some days that will, for some models, will stick out as being really bad residuals. And what I end up doing is I end up going to Google and being like, all right, we didn't predict the 4th of July well, so we over predicted that. And then there's this data point in March 12th. And I'm like, oh, what's that about? So if I just do like Chicago, March 12th, there was a huge Trump rally in Chicago that day, and there was a counter rally and a bunch of fighting. So let's say if I put trains in there, I can figure out that, oh, well, that didn't help. It turns out that they shut down the trains early that day because of riots, basically. So this question of like, what do I do about this? I know why the prediction is not good. We thought that there would be more people riding that day. It is I forget what day of the week it is. Let's see, is it here? It's a Saturday. But the thing is, I can't really put an indicator in the model for when there's going to be a riot. There's a bunch of examples like this in the data set. One particular example is when there's a Linkin Park concert downtown and a parade for the Chicago Blackhawks, and that has the highest ridership out of all the data, but we can't really like make a feature out of that. So there is some question that I'm going to sort of punt on as to whether that data point should even be in the data set, because you're never going to predict it well, and it might be sort of damaging future predictions because it's a very aberrant data point. I'm usually very loath to get rid of data. Unless it's like incorrect data, I would probably keep it in and find a way to deal with it. But anyway, again, looking at your data is really important, and figuring out if there are things here that you need to add new features to. So then, now that we know what we want to do in terms of what the tuning parameters are, what we can do is we could, like the very, very last model fit for GlobeNet would be the one that uses the entire training set. So what we could do is we could take our recipe, prep it on the entire training set, and then we can finalize the model by splicing in the actual values. So what finalized model does is it takes the model specification that has those values of tune in them, and it substitutes the values that are in this tibble with the best results. So instead of the penalty saying tune, after I splice these in, you can see these are the values that it found to be optimal based on our tuning process. And then we can create that last fit using the recipe and the final tuning parameter values. As you'll see when we get to the Mars model, this is a little bit kludgy. We have separate models here, separate objects, and using a workflow here is more simpler and probably preferred, but you don't have to use a workflow. The advantage of using the workflow is you only have one finalize call, and you don't have to worry about prepping and juicing the recipe. It does that for you. So you'll see that when we get to the end of the Mars modeling portion, that it's a little bit easier to do. So again, finalize takes the values that you have chosen to be best and puts them back into the model specification. And then once we have this final fit, we can print that model out. It does a little bit of printing at the top to tell you it's a parsnip model and how long it took. And then this is just the output you would get for the actual GlibNet model. And so you still have the actual GlibNet model fit that you can use for various things. So there's a little bit more to talk about this, but are there any questions about this part? All right. So you can use the actual GlibNet object. So the class of this object, GlibNet fit, is actually a model. It's called model fit. That's its class. It's not, it itself is not the GlibNet object, but the GlibNet object is inside of it. And the place it is inside of it is, if you use $fit, then the class of this is the GlibNet object. So you can use this for printing and plotting, any of the things you would do with GlibNet. The thing that I would beg you not to do would be to predict with it. And the reason would be, for example, if you try to predict with it, it might be problematic because, like, if the data you give it hasn't been centered and scaled the same way that we would center and scale the data, you would get answers, you would get values back for predictions, but they wouldn't be right because they're using, let's say, the original units and not the centered and squared units. So if I could find a way to disable this, I would, but I can't. So don't predict with it. Otherwise, you could use like the GlibNet plotting function, and what that does is it gives you a plot of how the coefficients change as you adjust the penalty. This is a really interesting plot. The problem is, and this is my opinion, so like, your mileage may vary or your taste may vary. I kind of hate it because like the substance of it is good, but I kind of want to know what this was, and I kind of want to know what these are. And, it's a base R plot that you have trouble coloring differently and doing things to. So I'm frustrated that we have this, potentially interesting plotting method, but it's not implemented in a way that's very useful. And so just as an example, here's some code that we can make the same plot, but using, let's say, ggplot in tidymodels. So we'll just walk through this a little bit. Just as an example of using these models in tidymodels to do things. So there's a broom method for GlibNet. And what that would do is that gives us, for all possible penalty values, it gives us the model coefficients. So when I run this tidy method on the GlibNet fit object, what it does is it gives me a very, very long tibble, and there's a column for the penalty, which is called lambda, and there's a column for which term it is. So whether it's, day of the week or ridership from Chicago, or let's say ridership from any particular station, it gives you the GlibNet model coefficients across all these different penalties. And so then what we could do is, since we have our best penalty, that one might not be in the data that we get back from tidy. So all this little code does here is it finds the lambda value, the penalty value from the GlibNet object that's as close as possible to the one we ended up using. So it just basically finds the one that's closest. So then we can take those GlibNet coefficients, we're going to plot, or we're going to use their absolute values. What I also want to do is I want to label some of the points on this line, right? So I want to know what these are. So what I'm going to do is I'm going to locate the, for the penalty value that I have, I'm going to figure out which of these lines are the furthest away from 0, and maybe take like the top like 5 or 6 or 7 lines and put labels on them. So I don't need to label the ones that are all down in here. I probably want to label this large negative one, these large positive ones, and maybe these 2. So what this code does is it basically gets the absolute value of the coefficients. I just looked at the plot and said, well, let's get the ones that are above an absolute value of 1.1. You can change this to be whatever you want to select more or less terms. We get exactly what terms they are, and then basically we subset the data for just those terms. So what I've done here is I've selected the data out that are only the ones, whoops, spoiler alert, only the ones that have these large absolute values. So that data frame I just made only has probably like 4, 6, like 7 or 8 rows. compared to the larger set. So then we can do some ggplotting. So we take the larger set of coefficients, we plot their penalty value versus their parameter values. We group them by term, and that's what gives us those lines for every term. And then we can color them by term so that we can differentiate them. And then we'll also apply sort of a special label for them. And the label is going to come from the special data set that has the ones that we want to highlight. We can create a vertical line for the optimal lambda, because a plot is going to be across all lambda. And then the magic happens here, down here, is we use this package called ggRepel, and that's where we plot the labels. So what ggRepel does is it looks at where the plots or the points that you're plotting are, and it positions the labels in a way that overlap the least. So it finds a way to show the labels where they're not sitting on top of each other. And so if they're far away from the data point, it puts a line between the data and the label. So this is just a really nice way to label those large coefficients without them sitting on top of each other and not being very readable. So if you were to run this, you'd get a plot that looks like this. So we can see that the day of the week, the weekday values, we have Monday, Tuesday, Wednesday, Thursday, Friday. That's the set of predictors that are up here. So you can see they have a large positive coefficient. So, that means it's, adjusting up the prediction based on whether, when, it adjusts up the prediction value for things that are during the week, which makes a lot of sense. You see Clark and Lake is this yellowish value that has a pretty strong coefficient. This makes sense. This is the 14-day lag of the actual station that we're trying to predict. So that's not surprising. The year makes sense also. We know when we did that initial plotting that ridership overall is like slightly increasing as years go by. So we have a nice positive coefficient there. And then Harlem is a sort of anti-correlated train station that seems to have a big effect. And what this means is the more people rode, or the more people who went into the Harlem station 2 weeks ago, the smaller the number of people that went into Clark and Lake. They're not too far from each other. So this would mean like if more people went in here, they probably did that in lieu of going to the Clark and Lake station. So in a way, it makes sense. This dotted line is the actual penalty value we ended up using. These plots I always found to be like really interesting. And so,
Max, are you using the a dev version or the current? Because we did update the tidy version for GLMnet recently.
No, this is independent of that.
Okay.
So we updated the tidy method for the parsnip GLMnet models. This is calling the actual Broom GLMnet function, which didn't get updated. So it's a difference of calling Broom for the GLMnet object versus calling Broom for the actual parsnip object, I believe. But maybe I'm wrong. I'll check this out at the break.
Sounds good.
Okay, sorry. Okay, I see the point in the Patrick. I'll look at that in at the break and let you know. The sort of the thing that interests me about these plots is how something like Clark and Lake could have, it's a decreasing value as the penalty increases, and then at some point it starts increasing again, and then another point it starts decreasing again. And kind of in a way it makes sense. You see these sort of changes as things come and go outside of the model. So you can see Clark and Lake has a decreasing effect until you get rid of Harlem. And then once Harlem is eliminated from the model at this penalty value, Clark and Lake, increases more and more. And then you'll notice it starts to decrease once the weekday indicators leave the model. So, the trajectory of these things don't have to be monotonic. Like you can have some things, it's unlikely that something's going to go to 0 and then get resurrected and come back. That could happen, but it's unlikely. But they're not always directly going towards 0. So yeah. So one last thing about the GlimNet model is you can compute variable importance scores, which for GlimNet and linear regression and logistic regression, these are usually just the absolute values of the coefficients. Now remember, when we run the GlimNet model, we have to put all the predictors on the same scale, so the regularization makes sense. And so since these are on the same scale, we can look at their coefficients and make apples to apples comparisons. I implemented all this stuff in Caret, and I thought about how to do this in tidymodels, and somebody already beat me to it. So there's a couple packages that do this, but there's this nice package called VIP that you can use, and this will compute the model-specific importance scores. So if I say, take my GlimNet object, give me the importance scores for the top 20 predictors for this penalty value, because again, the coefficients change over penalties. You can see that, and you can see it here also, the terms of the logic effect on this model were the days of the week, followed by Clark and Lake, the year. And this one, Belmont, shows a little bit higher than, where is Harlem on here? I'm not sure where Harlem went, but you can get basically an assessment of these things. If they have a negative coefficient, it'll color them differently. So you can see which ones are positive and negative. Another package that does this pretty well is the Daleks package, which has some things besides the coefficient values that uses importance scores. So that's an option also. We've been working with the maintainer of that package to make sure that recipes and all that work well with Daleks. And as far as I can tell from the testing I've done, it does. So that has a little more options than VIP does. So you can do that also. So, if I were doing this like for a living, you'd basically have this choice now where do I keep trying to juice linear regression by figuring out better features, and maybe there's some nonlinear things I could do. You could keep basically making the linear regression model more complicated. The other thing you could do is you could try a different model and see if there are other models that just more easily adapt to these data. So you could, I'm a big fan of taking something like linear regression, making it very, very performant, which a lot of times is not hard to do. But you could also just try something else to see if it works. So what we'll do is we'll start using Mars next as a model to see if that does better than linear regression does. Okay. So I'm guessing from the comments that this is maybe run on the CRAN or an old version of Parsnip. So this, yeah, I'll check this out and update the slides. I feel that I think maybe if you do GlimNet fit $GlimNet here, you'll get the same thing that I do if what I'm reading is the case.
Yeah, in RStudio Server, we have the old version of Parsnip. And so folks are using the new version of Parsnip, and this doesn't work with the new version.
Yeah, so what I would suggest for them is to maybe change just to GlimNet fit $fit. So that would definitely run it on the GlimNet object, and that would give you, the right columns. So give that a try and let me know if that was a solution, and I'll update the slides like during the break. Okay, so that worked for at least one person. All right, great. I will update that so we go out of the box with the right slides. All right, so we're going to kind of leave. That's what you would do. We're going to leave linear regression now in GlimNet. So any other questions about that methodology or how we tuned it and so on? Okay. So, one thing that we did here is we used grid search. And again, with grid search, you have to pre-specify what the submodels or the tuning parameter values you want to check out. Like you have to say ahead of time, these are the things that we're going to evaluate. So we're going to walk through the Mars model in a second, tell you how that model works, and then we'll look at doing sequential optimization, where it uses like a search routine to try to find what the tuning values are that we should evaluate to see if they're good. So we'll be switching gears in a couple different ways. All right, so MARS stands for Multivariate Adaptive Regression Splines. It's kind of it's probably in here because I like it a lot. It's an incredibly useful model. It's an old model. It's been around for quite a long time. There's multiple R implementations of it. And it's a kind of a cool model because, as you'll see in a minute, what it does is it makes some like nonlinear features of our original predictors and puts them in a linear regression model. So all the model estimation parts for coefficients happens using basic logistic regression. And what it sometimes can do is it could give you a model that is on the order of the same performance you would get through, let's say, a neural network or random forest or something, but it might be very, very interpretable. So one cool thing about Mars is because of how it's structured, you can very often show the model to somebody and show them exactly how one parameter affects the predicted values. So I've sat down with clients and with this really seemingly complicated Mars model and shown them like profile plots of, well, this predictor doesn't affect the outcome until you get to a value here, and then the influence of that predictor takes off. It can do some really neat things in terms of interpretability. Anyway, so let's talk about what it is. So I mentioned it uses some nonlinear functions, and it uses something that's kind of like a spline, but it's not. We originally called them hinge functions, and you'll see why. If you're into the neural networks, they were rediscovered by the neural network people and call them ReLU, or rectified linear units. So they've sort of rediscovered these special types of splines. And what the nonlinear function is if let's say you have a predictor like ridership at Clark and Lake. So what the nonlinear feature needs is it needs a split point for that predictor. So let's say the split point is like 3.5. So what Mars does is it creates a new feature based on the Clark and Lake predictor that below 3.5, that new predictor is 0, and above 3.5, it's exactly what it would have originally been. So that's what this hinge function does, is it zeroes out one side of the predictor range. And that would be, let's say, the right-handed hinge, because everything to the left of the split point is 0. And then its sort of pair would be a left-handed hinge, where everything above the split point would be zeroed out. And then below that is the actual data value. So what Mars does is it does this search through all the data, all the predictors and all the values of the predictors, and it tries to find for a single predictor what the best split point is. And so let's say it chooses Clark and Lake as a split point, and let's say it chooses like a value of 3.5. Then what it does is it creates these two paired hinge functions and puts them in a linear regression model. And then it just fits that model like it normally would, with an intercept and then two slopes. And so what that does, it creates a kind of what we call a segmented regression. And what Mars in effect does is, and you'll see this visually in a few minutes, it takes these predictors and isolates the range of the predictors, where in parts of the range of the predictors, they have no effect, and in other parts, they have an effect. So it creates almost like these hockey stick type models that are linear between the splits and 0 otherwise. So let's show, maybe instead of showing you a function or some equations, how this actually works. Here's some data I simulated. Here's the nonlinear function. It's basically an exponential. So if we were fitting this model, it's clearly nonlinear. So regular old LM wouldn't do well with it. But what Mars would do is it would go through every data point here. There's only one predictor, so we don't have to search across different predictors. But it would find a split point of these data where it makes the most sense to isolate one side or the other of the range. So it turns out if you do the search initially, the split point it comes up with is about 0.6. And so if you look here, it's about, I think it's about right here is where the split point is. So what it does is it creates like the right-handed hinge where below that split point, all that predictor's value is zeroed out. And above that split point, you get, just X, what you would have gotten. And then you put that with its pair, which is 0 on the high side and the original predictor on the low side. So what happens is when you put these two terms into a model, a linear model, you get regular old coefficients for them. So when I look at this, this is, let me make sure I get this right. This is the right-handed hinge, and X minus this is the left-handed hinge. I may have gotten that wrong. But you can see their coefficients. Now this, what this doesn't really have any interpretive ability, but when we put it in the model and plot the predicted value, you'll see what actually happened. And that initial phase of the Mars model looks like this. So what it is, it's an intercept. So at some point, here's where the intercept is, where X is equal to 0. And then if you look at the coefficients, the negative one here is for this hinge. So it's a negative when you're below the split point. So negative slope here. And above the split point, it's a much larger positive coefficient. So you can see that coefficient is 2.4. So what it's basically done is it's created linear models, but they have different slopes on either side of the split. And the split was chosen basically to give you the best fit for these data. So this isn't great, right? So it does decent down here and does okay sort of around here, but once you have this inflection point, it's definitely not working very well. So just as the first phase of Mars, like on the first iteration of Mars, where it only looks at 2 features, this is what it would produce. But what it would then keep doing is it would keep adding more and more features. It would take these 2 features and then say, well, given that we have these 2 in the model, where's the best split point I can add so that I have another sort of split point here to model different slopes on all the different combinations of the ranges. So if I go for a second iteration or a third iteration, it's going to keep looking at this and start adding split points to this data and try to generate different slopes between the split points. And so the way Mars grows is it keeps adding these things as it goes, but then at some point it does something called a pruning phase, where it looks at the split points that it has and says, well, I do have a coefficient for this split point here, but it's not really significant in the model, so maybe I should take that out. So even though the model grows these terms in pairs, it may get rid of one or perhaps both of them as it goes along in pruning. There's different ways to do the pruning. You could have it grow them all and then prune them all. You could have it sort of go stage-wise where it adds 2 terms and then sees if they should both be there, maybe does the pruning along the way. So there's some options when you do Mars to figure out when you do the pruning and how. And then the way it does the pruning is this tool called generalized cross-validation. So way back in the day, before we had a lot of access to computers, for linear models, some really smart people, like this lady named Grace Waba, came up with this linear algebra method that gave a very good approximation to what cross-validation would give you for an error rate, but you didn't have to refit the model. So this GCV method is like a shortcut to cross-validation, and it's only useful for linear models. And remember, I mentioned, even though we have nonlinear terms here, all the parameter estimation is done using LM. So it's just a regular old linear regression. So what it can do is it can basically, without refitting the model, in effect, take this term out and see if the cross-validation statistics get worse. And if they do, it keeps it, because getting worse means that was required. So if you got rid of this term and the cross-validation error rate didn't change any, you're like, oh, we don't really need this because it doesn't matter to the model. So it uses this generalized cross-validation method as a way to prune the terms as it does its fitting. okay? So this, let me come back to this next slide for a second. If we were to keep doing this, what we end up having is a Mars model for this simulation that has 4 terms in it. So it has a split point for the one we first saw. It has a second split point at 0.77. It has a third split point at 1.2. So you can see there's a split point here that came in with a pair of hinges and it got rid of one. Same thing here, 2 hinges came in and only one. And then the original 2 that we started with are retained. And so what happens is these coefficients get combined to make up the coefficients between the split points. So you can see we have a really large negative coefficient on the rightmost panel. That's mostly associated with this. The coefficient that's in between here is a combination of more than one coefficient. Same thing here and same thing here. And I actually sat down and did the math on this. And so if you look at how these model terms affect the actual slopes here, what it looks like is that the first 2 model coefficients that we created are the ones that are here and here. So the only coefficient that affects the slope to the left of the smallest split, so this region, is this one here. And then if we're looking at what coefficient affects the range between these 2 splits, it's its corresponding pair here, which had a positive slope when we first fit it. But then if we look at between this region here, it's the combination of the slope for this term and for this term. And then you can see this large negative slope is a combination of this term, and this term. So you don't necessarily have to figure this math out whenever you do this. I'm just trying to demonstrate what Mars is doing. Mars is isolating different regions of the predictors. In this case, just one predictor, but it's isolating a different region of the predictor and then producing linear models in between there. And even though they're very stick-like, right? There's not like a smooth like transition here. They're discontinuous models in a lot of ways. They can very easily adapt to very, very nonlinear data. So the cool thing about Mars is if your data are linear, like actually have a linear effect, it can just put the original term in without any splits. But if you do have like a nonlinear term, it's only nonlinear in, let's say, one predictor, it can adapt to that predictor's nonlinearity and not enforce that type of nonlinearity on some other predictor. And it does that using these sort of like segmented stick models. So, okay, I'll wait for a question. Oh, okay. Can you get the output as non-overlapping coefficients, or do you necessarily have to work them out yourself? Yeah, you don't. So what the model would give you would be this. It would give you model coefficients for this term. If you wanted to know what the slopes were within here, there's probably a better mathematical way of figuring out than me just sitting down and writing out like where these regions are. The package we use for this is called the Earth package, because at the time Mars was a trademarked term. The Earth package has a lot of tools in it for this model. It's very well developed. I wouldn't be surprised if the developer has something that would produce not this plot, but that would tell you what coefficients affect what. And if he didn't, I bet if you asked him, he'd produce one. Is there another question? Okay. Is this similar to GAM? Yeah, in a vague theoretical way. So what a GAM is, it's a generalized additive model. The model I just showed you is an additive Mars model, meaning it only models one predictor, like in a feature at a time. But as you'll see in a minute, we don't have to have an additive Mars model. Technically, this is a single. It's a spline with a known split point, like it's a 0 degree freedom spline basically. So GAMs usually use splines. So there's like a vague connection between this and GAMs, but apart from that, not so much. The fitting methods are different, and you know, when you look at the model fits, they don't necessarily look the same. Another thing about this that I'll go into a little bit that is not true of GAMs is when you run a GAM model, your model uses every predictor. One interesting thing about Mars is it only uses the predictors in the prediction equation that we're split on. So we might come in with like 1,000 predictors, but in the course of building the Mars model, if it only splits on, you know, X, Y, and Z, its feature selection ability got rid of all the other predictors except for X, Y, and Z. So Mars, as you'll see in a little bit, automatically does feature selection when you fit the model, whereas a generalized additive model doesn't. So there's some mathematical connections to them, but they're tenuous. I mean, they're real, but they're not very strong. Maybe it's a better way of putting it. What's the interpretation of the coordinate shift? I can understand it's at this point in time this happened, but obviously that only works with time. Is a better interpretation apart from its splits here. So the split points are usually associated with curvature, right? So there's no utility for it to split in this region because there's no bend here. So the split points usually tell you something about where the curvature is. So let's say I had like a ton of data and I tell it to do like 500 splits. It would end up adding a bunch of like splits that are right around here, and it's trying to approximate the curve here without it being so blocky. And so the split points would tend to associate where there's the most curvature in your predictor. So that's the main relevance of them. Is, you know, you don't see split points where there's no curvature, basically. Yeah. There's one more question, I think. All right, I'll come back to questions in just a minute. So I mentioned that, you know, Mars does pruning of these terms. So you can see here that actually at some point it generated a total of like 6 splits, but it only retained 4 of them here. So, so there's different ways to do that. The first thing you could do is just let Mars be Mars and use its generalized cross-validation tool along the way to make its own splits. And that works fine. It's relatively fast when you do that. The problem is I find it under splits. So I find that it usually uses less splits than it probably could have. And that's just to the mechanics of how its pruning method works. So another thing you could do is instead of using the generalized cross-validation, we could use the same cross-validation method that we've been using the whole time and just say, well, let's say the number of retained terms is the tuning parameter. So if we use GCV, GCV determines how many terms should be in the model. We don't tell it that. We don't say, give me 5. It just figures out what that number should be. So that's the first way to do it. That's like the internal Mars method. The sort of external way to tune this model would be to say, hey, don't do any pruning, but give me the best model with 8 terms, or give me the best model with 6 terms or 5 terms, or what have you. So, so I usually don't start with GCV. It works really well, but I find that external resampling does a better job of giving you a little bit better performance. And I think on average, it ends up selecting more terms, and I think those terms are useful. So what we'll do is we'll start with number 2 here, but I'll show you how to do both. And I might actually run the GCV fit here also. So I'll show you the different approaches of doing that. Yeah. So the other question was about like the split points and where they are. And it says, in terms of interpretation, I'm thinking about a variable like years of education, where it has a very different effect at different points along its range. Yes, so I agree with what I think you're saying is, parts where that predictor becomes important is probably where the splits are going to go. Either that or, because that would imply maybe curvature of some type. And so like here's a region where it's clearly important, right? It definitely has a large slope. So, but you wouldn't get splits in here. So it might be the splits bracket the changes in performance a long time. So like this has the largest slope of the model, like of the range of the predictor, but there's no splits in here. So it's just saying in between here, we should have a different slope. So I think maybe I'd interpret it that way. Anyway, okay. So so again, it's segmented regression, but this is only for one predictor. So what happens when we have multiple predictors? So what could happen is when it goes to do this search every time, what it does is the first thing it does is it evaluates all the predictors with no splits. And what this means is if like you have a completely linear effect with no curvature, there's no split point that would make a lot of sense. So it puts the original predictor as is as a potential candidate. So it may look at like 100 split points along that predictor, but it also compares them to just the regular old linear term. And so this model needs dummy variables from qualitative predictors. And so that's basically how dummy variables work, is it doesn't try to split them at 0.5 or something like that. It basically puts them as a linear term, and they're sort of outside the splitting part of it. But if it thinks that that dummy variable is the most important term it could put in the model, it will put it in there. It's just not trying to split on binary data. As I already mentioned, it does feature selection. So if you never use a predictor in any of the splits, then it's functionally independent of the model. And this is a critical, like really important thing for models, that if you don't know a lot about the predictors and what's important, Mars can help you learn what's important to the model. When you have multiple predictors, it could split on any of them. So, sometimes the split will be associated with like the weather or Clark and Lake or, the Bears at home or not. And there's ways to do, as you'll see in just a second, there's ways to do non-additive models where it considers product of split points between variables. So each split point, each hinge function only involves one variable. But if you tell it to do, for example, a second degree Mars model, it'll find like split points for the best predictor and then split points for the second best predictor. And instead of adding 2 terms of the model, that's 4 terms of the model. It has all combinations of the hidden points. And that has some interesting things that it does. I'll show you a plot of that in just a second. An additive model would be a Mars model that only split always on one predictor at a time. And then a second degree Mars model is not additive because it can split on a product of 2. And you control that. Like you control whether you want an additive model or a second degree model. And I'll show you how that works. But let's look at this bit here, where if we have like X and Y in different split points, what happens to those 4 hinge functions? What does that do? So I just took some data and just did like a scatter plot and invented some hinge functions for predictor A and predictor B. So if my split point for B happens around 5, I get 2 hinge functions for that, one where it's zeroed out above 5, one where it's zeroed out below 5. And then let's say I have A with a split point of also 5, but it's sort of on the edge here. And A would get zeroed out on one side of 5 and the other, depending on the hinge function. So if I take, for example, these 2 hinge functions and multiply them together, what I get is everything below B equal 5 gets zeroed out, irregardless of A. Everything above A equal 5 gets zeroed out. And then you have this like little quadrant in the middle that has non-zero values. So what happens when you have 2 numeric predictors and a second degree hinge function is it's isolating these 4 quadrants of the data based on where the split points are, and that there would be a linear slope for this region, the same way there would be a linear slope for the reflected region below it, and then different slopes for the two regions over here. So what it's doing is it's isolating bivariate subsets of the data and modeling those in a different way than other regions. So it's nice, like in the Ames data, there's some interesting things where there's times when, for example, adding the number of bedrooms to a house can decrease its price, which doesn't make much sense if you think about it. Like usually as you add bedrooms to a house, the slope on that should be increasing because sale price should be increasing. But it turns out that when you run a Mars model on this and a few other models, what Mars can do is it can isolate a region where you have some houses with very small square footage. So if you have like a house that has like 1,000 square feet, but has 4, 5, 6 bedrooms, that house is all bedroom. It may not sell as well as a larger house with that many bedrooms. So it's almost like an interaction effect. So what Mars can do is it could isolate certain regions of your parameter space where the slope should be going in a different direction, or maybe a slightly different magnitude of the direction, and pick up on those nuances in the data and model them appropriately, instead of just always enforcing that the overall slope for a number of bedrooms should always be increasing, because there are some data subsets where maybe it shouldn't be. So that's one really nice thing about this second degree bit. All right, if Mars doesn't split on a variable, then it won't be included in the final model. So let me go back to slide 52. Yeah, okay, so you're right. My terminology is a little off there. I should say if Mars never uses a variable, either with a split or by a linear term, then it's not part of the prediction. So you're right. It could not split on a variable, but use it as is in the model, and it would still be included. So thank you. That's a very good point. Yeah, sorry for the confusion. All right, so how would you do this in R? There's a package that's been around since the S days called MDA. It has the original Mars function, but the Earth package is a little more modern. It uses C to do the computation, so it's faster and it has more features. It has a function called Earth. You could either use a formula method or the non-formula method. It allows you to do either one. It has some parameters, the main ones being these 3. NK is the total number of terms it might make before it does any pruning. Nprune is the number of terms it should keep after pruning. And then P method is the pruning method, which could be either like forward, backwards, or stepwise and things like that. Sometimes people ask me like, well, what's the effect if NK is large and Nprune is small? And the answer is, man, I don't know, because it really depends on the data set. And the interaction between these tuning parameters can be really, really hard to predict. So the author of the package has written like a technical document that I've linked here that talks about this a little bit. It's not trivial, but so that's one of the reasons why we would like to tune at least 2 of these. So we're going to tune over these, or at least fix these values. I usually don't mess with NK because I've found it doesn't do much to the model fit. And again, NK is the total number of terms that it should start with, like what the upper limit is. It does have a variable importance method. So what it does is every time it adds a new a variable to the model, it figures out how much the cross-validation statistic changes and it records that. So if you have, let's say, 5 terms that use Clark and Lake, it accrues the total amount of change in GCV as you added that. And the aggregate value across those individual model terms for that predictor is how it sort of accounts for importance. So if you never split or used a variable in any way, it would have an importance of 0. You could have a predictor that gets used a lot, but in little ways. And so that would be contrasted with a predictor that gets used once with a big effect. So it just kind of like accumulates the change in performance as you've added stuff. So if you want to use this package, you can do that directly. We do have a parsnip method for it. So there's two ways we could do it. If we want to let GCV do its thing, then we can just tune on the product degree. So product degree is either 1 or 2, 1 being an additive model and 2 being a potential interaction model. I think you potentially could use 3, but I think computationally the thing would take like years to fit. So traditionally we just use 1 or 2. So if you do this, you're not optimizing directly the number of terms that are in the model. Mars figures that out using GCV. But if you do want to say what number of terms should be, then what I suggest doing is having number of terms be a tuning parameter. You can tune over the product degree, and then you can set the printing method not to be tunable, but to be none. And what this says is, I don't want you to take any out. Let me use my own cross-validation to decide how many terms should be in there. So that's what we're going to try to start off with. The only engine we have implemented is Earth, which is probably stay that way. And then Mars could also be used for classification. So it has like a logistic regression analog. We're going to use it for regression, so we have to set the mode to be regression. So this is the model part of the Mars fit. So then is there anything that we need to do with predictors? Well, I do mention that we can make dummy variables and give them to Mars. Mars can make them itself if you wanted to. But for this data set, one of the problems is that we have a lot of correlation in the data, right? So we have all these 20 columns of station data that we know have correlations in the order of like 0.95 and above. And so that might be kind of harmful to Mars. So what we'll do is, instead of giving it the original predictors for the stations, we can try to give it the principal components instead. So we might only need like 2 or 3 principal components to get uncorrelated representations of those station data. So since there's such correlation in the data, we can use probably a relatively low number of principal components to get the same information, but those components are uncorrelated. And that might do better in the Mars model, but we're not sure. So what we'll do is we'll take our original recipe that had the holiday indicators and dates and things like that. We'll start with that. We'll normalize those. We'll normalize the station columns, and then we'll add those to PCA. So we're only computing PCA on those 20 station columns. We don't know how many components to use, so we're going to tune those. So I'm going to have a tuning variable that's a number of PCA components, and then another one that's the number of Mars terms. So I might like have a Mars term that involves PC3, the third principal component, and PC3 is made up of all of the original station data. So so we almost have like different levels of where the variables contribute and how they contribute. So what we could do, well, so one thing before I go on is we did a little trick in step PCA that if you say I want 0 components, what it will do is it will not do PCA at all. So if we do like 1 component, it'll do PCA and give you 1 column back, 2 components, it gives you the second principal component and the first component. But if I say numcomp equals 0, it doesn't do PCA and just gives you the original data back. And you might wonder like, well, that's kind of weird. Why would you do that? And the answer is, if we don't know if PCA is the right choice or not, we might want to have a non-PCA option in the same tuning process. And having 0 components be non-PCA is a way to do that. Because otherwise, what you'd have to do is you'd have to have one recipe with PCA and another recipe without PCA and do separate tuning runs and then compare them. And this is just like a little shortcut to do that. So if we find that our tuning would prefer a value of 0 components, what that's saying is that it would prefer you not to do Mars at all. Or, I'm sorry, not to do PCA at all. Use a Mars model with the original predictors. So that's the tuning aspect of this. Any questions about how I've done this? So we're going to use our manual method of determining the number of coefficients that are used in the model. We're not going to do this, at least not right now. So we'll do this in combination with this recipe. Will the original variables be removed automatically if PCA is added? Yeah, so if components is greater than 1 or greater than 0, it replaces the original columns with the principal components, so it would get rid of them. Now there is, I believe, let me double check, I believe we added an option to PCA, so let me check. We're going through different steps and seeing where we should add this. I thought we had done this for PCA. Let's see. No. So there have been requests to add like an extra option here to have retain equal true, because sometimes people want to do other things with the original variables after PCA is done. Honestly, I don't know what that would be, but I thought we'd implemented that. But there is an issue out there to add that for various steps. So I'll try to remember to go through that, because I swear we did that. Maybe it's in the development version, but I don't think so. So, but the answer is right now, yes, it would replace them with the components that are generated. Okay. Okay. So one thing we could do if we wanted to is we could do grid search again. We could give it like how many terms we think it should do. We could give it, a 1 or a 2 for product degree. And then we can go up to, I don't know, like 0 to 20 components or something like that. But just for demonstration, we're going to try something else. So try to remember, like, we're going to sort of segue into a different optimization method and then come back and show how we're going to use that optimization for Mars for a little bit. So we're going to kind of like walk away from Mars for a few minutes to talk about sequential optimization. So, so again, grid search is a situation where we predefine everything and then figure out what's best from the things we pre-specified. When you have a lot of parameters, sometimes that might be problematic or may not be efficient. But on the good side, like, we can parallel process our hearts away. Between that submodel trick and parallel processing, there are a lot of situations where we can make grid search, fairly efficient. But if we specified the grid wrong, or like we didn't cover it well enough, then there might be the question of, like, did we get a good value, or did we have to spend all day trying to get a good value? So what the iterative search methods do, there's a bunch of them. The one I'll talk about the most is called Bayesian optimization. What Bayesian optimization does is it takes your current results. So let's say you have like 3 or 4 data points you've already evaluated, like 3 or 4 tuning parameters you've already evaluated. What it will do is it will build a model on those where the Y, the outcome of that model is performance, like in this case, RMSE, and the predictors are the tuning parameter values. And then it builds a little model, and then it evaluates a bunch of different combinations of tuning parameters as candidates, predicts what it thinks performance would be, and the one it predicts would have the best, like in this case, the lowest RMSE, would be the parameter value that it evaluates next. So what it does, it takes the existing model and puts like a model on top of that, and then makes predictions on every iteration of the search. It predicts a different tuning parameter or combination that should be attempted. And then we use resampling to evaluate that. That data gets fed back into the model and so on. So it's more flexible in terms of like how the parameter space is explored. Theoretically, it would avoid exploring parts of the parameter space that are not great, right? So like grid search is going to search a wide range. And so it's going to spend a lot of time building models for regions that just aren't that good. So as I was just saying, one of the values potentially of iterative search is that theoretically, it doesn't spend time looking through parts of the parameter space that that don't merit search. So so that's good. But on the other hand, we can't parallel process as well with this as we could with grid search. So since we're like going to suggest a new parameter to test, we can only like parallelize only if we're testing one parameter at a time. we can only parallelize the estimation of that particular parameter. So, so there is some like loss of parallel processing efficiency using an iterative optimization. Another aspect of this is like we build this probability model on top of our existing resampling results. And so the question is, if that model takes a long time, then the efficiency goes down. So if it takes a long time between evaluating new parameter points, then the overall efficiency of iterative search goes down. The model that we'll use is called a Gaussian process model. And that model is not, I mean, when you have a lot of predictors, it's not especially efficient. So sometimes the speed of iterative search is offset by this Gaussian process model. It's as fast as we basically can make it right now, but in some cases that would be not very fast. Again, any search procedure could be used. I have a repo from years ago where I show how to do with Caret, genetic algorithms and simulated annealing and some other things. Within tidymodels, we've implemented Bayesian optimization in the tune package. I have another package called fine tune that will have simulated annealing in it. And that's working right now, but I'm working some of the kinks out of it. So if you really want to try simulated annealing, you can do that by trying this package. Otherwise, the one we have implemented right now is Bayesian optimization. And that's what we'll focus on today. All right. So how does it work? So it takes an initial set of results and then builds a model from those results to predict what the next set of tuning parameters should be. And so the question I get is like, well, what makes it Bayesian? And the answer to that is it's fitting this type of model called a Gaussian process model, which is inherently Bayesian. If you don't know much about Bayesian analysis, in a nutshell, what it does is, our linear regression model and all these models have these parameters like the slopes and intercepts that we try to estimate. And when we fit like ordinary least squares models, we don't really say a lot about the distribution of those parameters. But in Bayesian optimization, what we do is we put a probability distribution, like a definitive probability distribution on each one of our model parameters. And in doing that, the way we estimate the models are different than how we would do that with non-Bayesian models. And there's a lot of benefits of doing that in some cases. And it just turns out that this Gaussian process model happens to be a Bayesian model. Now, the main functional difference that we get from Bayesian models is when we go to make prediction about what the performance would be on a new tuning parameter value from this Gaussian process, we get a mean prediction. So we might say, oh, if you tried 5 Mars terms and 2 PCA components and an additive model, we predict that the mean RMSE would be like 1.1. And then we also get a variance prediction. So we can say what the variation around that model prediction is. And that will be used when trying to figure out which combination we should evaluate next. So you'll see that in use in just a minute. Okay. So like here's just like a little mock-up of how this would work. Let's say we started off with 5 Mars submodels that we looked at. And let's say here are their resampled RMSE values. Then what the Gaussian process model does is it treats the RMSE values as the outcome and the tuning parameters as the predictors and builds this model to then make predictions for configurations that we haven't looked at to see which one is at least predicted to be best. And then it would then acquire that data point, resample it, and then you'd have another row here for that data point that then you would put into another model and so on. Yeah. So if you've never heard of this model or you would like to know more about it, it's in some ways similar to support vector machines in certain mathematical ways. If you're looking for a book, there's a really concise book that you can get in PDF here. That's a great place to start. This is the one basically that I learned from. And so there's not much to know about fitting these models. I mean, there are different ways to fit them. In actuality, the Gaussian process itself has tuning parameters, but they have relatively efficient ways of estimating what their value should be. So generally speaking, you can change the parameters of the Gaussian process model, but a lot of the internal methods it has for figuring out what that should be work pretty well. So I'm not gonna mess with that part. So the trick that makes this model useful is it has this thing called a covariance function of the model inputs. And so imagine, like when we talk about Mars, we showed like a single variable. So imagine like we had a single tuning parameter and then we had performance. And so what this covariance function says is, what is the variance function over the range of that predictor? And so the one that's typically used is the radial basis function variance parameter. And what it does is it says, as you move away from observed data points, and data points here would be tuning parameter values, as we move away from those observed measured values, the variance explodes sort of exponentially, right? So this should look familiar to you as being part of the normal distribution. But what it means is, as you get further away from the actual data points you've observed, the variance increases very, very quickly. And when you get closer to them, the variance actually gets very close to zero. So you have to specify like a variance function that says, well, compared to data that I have, how should I compute the variance across the tuning parameter range? And that's something we set up front. And this radial basis function is the one that's used most often. There are others you can use, but this is the one that's typically used. I'll show you what that looks like in a second. Like, you can see the quadratic nature of this in just a minute. So what we're going to do is we'll build this, or we'll build this Gaussian process model. It'll make mean and variable or mean and variance predictions for new tuning parameter values. In that variance function I just told you about, basically the variance will be very large for tuning parameter values that are not close to the ones that we've already measured. So, so very often the variance in the predictions for tuning parameters are driven, for the most part, by how close they are to the ones that we've observed. So just let me show you like a visual example of that. So let's say we just have a single numeric parameter and we're trying to maximize R squared for the model. And let's say we started off with like 3 tuning parameter values. So here's the tuning parameter. I'm doing it in a log scale, and I measured R squared at this value, and this value. So if we look at them, we'd say like, yeah, this is pretty close to, this is the highest value. That's the most interesting. So the Gaussian process model can be very nonlinear. And if you fit it to these 3 data points, what you'd get is a model fit that looks like this, that it goes directly through the individual data points. And here's the mean prediction in the line here. So you can see it sort of plateaus out here, and then it's sort of quadratic-ish as it comes here. Now, the regions around it are like the 95% intervals around that. And so you can see this explosion of variances as we get closer to a data point. That radial basis function variance term goes basically to 0. So the variance goes to 0 when we're at an actual observed data point, but in between data points, it's largest in between them, and it's best seen here, but the variance kind of explodes at the midpoint here. And then looking on this side, there's no data on this side, so the variance, since it's very spatially driven, it sort of explodes on this side to be extremely large. So if we were looking at this, here's our fitted model, we'd have to ask ourselves, well, where should we sample next? Like, it doesn't necessarily make much sense to sample out here, because our mean prediction says our R squared is not going to be terribly high, and it has a huge amount of uncertainty around it. So these region would be really unattractive. There might be a region in here that is more attractive. So we're going to talk for a few minutes about what they call it as acquisition methods. How do I acquire a new value of this parameter? So which one should I choose to sample next? And acquisition methods are functions of both the mean and the variance of the prediction here. So there's a few different ways of doing it. There is this trade-off between what they call exploration and exploitation. So what exploitation does is it wants to exploit the data you have already acquired. So exploitation would mostly consider the mean of the prediction. So if we were doing a pure exploitation model, we'd find the part of this mean function that has the highest R squared to be predicted, and that's probably going to be around here, right? So if we don't consider variance at all, we just pick the point on this curve that's largest, and that would be like in this region. Now, that's not necessarily great because it would always keep you right around the data points that you've already sampled. So sort of the opposite of exploitation is this idea of exploration. What exploration does is it starts to factor in the variance in a little bit. And it looks to say, like, for some combination of mean and variance, how would I pick the next point to acquire? There's different ways of doing exploration. So let's talk about one of them that was originally proposed. One would be maximizing a confidence interval. So if we want to maximize R squared, we might think about finding a data point that maximizes one of the bounds. So for example, if we look at these regions, here's like a close-up of the region here. If we do a bound that has a very, very small amount of standard error, that's the red one here. If we look at a little bit more standard error, that's the blue one here. It's very slight and hard to see. The other line here is the no variance. So no variance, I would pick maybe a value around right here. If I add a little bit of variance, I move a little bit closer here towards this one data point, because that's where the bound tells me is highest. And if I add even more variation, I actually scooch over more and more towards this data point. So it's hard to see because they're very close together, but choosing the amount of variation to add will change where you would maybe select the next point. But it'll be somewhere in this region. But the question is, like, how close to this data point do I sample? This is really intuitive conceptually, but in practice, I don't think it's especially great. It's not something that people use a lot. And I don't think, I've tried it a bunch, and you can use it in Tune. I've never seen it give me the best results. The acquisition function that people use the most, I think, is something called expected improvement. So one downside to this method is it doesn't take the existing best into account. So this formula defines the confidence interval doesn't show anything related to the current best value. And so one thing that expected improvement does is it takes the current best value and computes, based on the mean and variance, what it thinks where the most improvement would be in the model. And so here's some, you can look at the math, and there's a paper linked here. I think there's a paper here that you can look at. If it's not linked there, let me see. No, that links to the notes. That's weird. I can post the paper for this, or you could just Google expected improvement and see it. But it uses a combination of the mean and the variance. So here's the variance effect. It's here and here and here. And then the mean prediction comes into this delta function. So it's looking at the difference in mean between the current best and the predicted best, and then has ways of normalizing that using the variation of the predicted best. And so if this is what the confidence interval looks like as an acquisition function, what does this function look like for expected improvement? So if I take these data and calculate expected improvement, what I get is this. So expected improvement is very low down here because the mean prediction is very low. It doesn't matter what the variance is. But as we get closer to the best value here, the expected improvement comes up, and then the variance functions sort of take over here. And it turns out that the next value predicts is actually very close to the existing one. And then the expected improvement comes down a fair amount, and then it actually goes up here because the variation is making the potential for improvement higher here. So it's a very nonlinear function. Sometimes it's hard for me to conceptualize what it's doing, and it might look like it's predicting the best one, but it's just to the left of this current best. So if we just pick the one with the best expected improvement, we'd sample another point very close to this. We'd fit another Gaussian process model compute this curve again and figure out which one there is the best one. So let's say we do this process for another, I don't know, like 20 iterations. And here's what we get after 20 iterations, is we end up sampling a lot of data points in between those two best values. But somewhere along the path here, we ended up sampling values out here. At some point, it thought that the potential best improvement would be on this region out here, which didn't really bear itself out. You can see the variation's gone down considerably because we have more data points. It's still not sampling in this region because this data point is telling it it's pretty suboptimal. So it's basically been bouncing around between these two values and then jumped out here for a little bit, then came back and started sampling more in this region. So at this point, if we were looking for the next point to try, the expected improvement here is to the right of the best. So we'd start probably sampling down in this region and keep going until you told it to stop. So the nice thing about expected improvement is it's a mixture between exploitation and exploration. You can modulate that a little bit further. There's something that's like a fudge factor you can put in that says, you know, I'm not going to penalize the expected improvement as long as you're within some like percentage of the best value. So adding this tau value here is like a trade-off value, and that will make it a little more lenient. So by adding this tau value as like a fudge factor, will enable it to start exploring a lot more outside and away from the current best values. So if you're worried about it being too close to the actual observed optimum, then you can add that tau parameter and let it explore more. So one other thing that I've added for the tidymodels implementation of this is something I didn't really see anywhere else, and I think it might help periodically, is there's this field called active learning. And what active learning does is it looks to acquire, like we're doing here, it's looking to acquire new data points to improve a model. And one thing it does is it does something called uncertainty sampling. And what uncertainty sampling would do is it would say, where's a data point that that I don't know anything about? So give me a data point that's far away from the current data that I'm trying to use, and select that one as one to put into the model. So we're not really going to show it too much here, but you do have the ability to, if your model is not really improving, trigger it to just randomly sample something way outside the space of what you've already acquired, and maybe force it to sort of search a different region. And if you've been missing a region, you know, it might jump there or find a good value and then continue to optimize around that. I haven't really seen that done in the Bayesian optimization literature, but it's done quite a bit in active learning. So it's something we can try out if we really want to. All right, so to sort of summarize, Bayesian optimization is an iterative method. The requirements for it is, it doesn't need a grid, but it needs to know the range of the parameters. So like with penalty and mixture and number of terms and all those things, we need to tell it like, well, you should only evaluate candidates between a value of this lower value and this upper value. So it needs to know the range of the parameters. And if there's a transform scale, it needs to know what that is. It needs an initial set of resampling results so we can build the Gaussian process. If you don't have any, then you can just tell it, give me 5 or 7, and it will do like a space filling design to get those. Much like with grid search, you also need a resampling scheme. You need to tell it which performance metric to optimize, which would be like R squared or RMSE, and then which acquisition function. So the acquisition function we typically use is expected improvement, and then you need to tell it how many iterations to do. There are parameters inside of the function we'll use that says if you don't have enough improvement within, I don't know, 15 iterations, it will just stop. So it won't just keep going forever. So those are the ingredients. For almost all these things, we have reasonable defaults, so you don't need to specify too many of them. And the function that we'll use is called TuneBayes. So that will be our alternative to TuneGrid that'll do sequential optimization instead of grid search. So before I start running code, are there, excuse me, are there any questions? If I had more luck with iterative search versus non-regular grids and regular grids, yeah, I have a slide on that. So if you're cool with this, I'll table that until we get through this part. It's not like a hot take of mine, but at the same time, I think there are places where iterative search does best, and those may not be the places that we typically live. So, spoiler alert. What is known, even anecdotally, about whether the performance surfaces for hyperparameter spaces encounter in practice are really as smooth as using that kernel? Right. So the question is how smooth are these functions, right? So, we're using these smooth modeling functions to make predictions. Are they really smooth? I would say probably they're not. They're pretty smooth, I think. So I've done a lot of grid search, And in my last job, we had a cluster in a grid that had 2,000 cores on it. So, with the chemists that I work with, for some things, they wanted us to throw literally everything at it. So we did very, very large grid search sometimes. And so what we got is we could look over a large range of values using grid search, what those profiles are. As you look across the number of boosting iterations, what does performance look like? And it would be very unusual for it to be a weird nonlinear surface. So I think in general, the relationship between these tuning parameters and the performance is, I think more often than not, it's a relatively smooth and not pathological relationship. So let me just go back to this GlimNet example. For the models that we tend to use, or I've tended to use, they mostly look like this, where you maybe have them come up and come down. But generally speaking, there's a plateau where they work or they don't work, and then some region where they change in an incremental way. So this is more likely to happen. There are some that are quadratic, where they go down and then they come back up. But I've never seen anything that looks like cubic or like a sine wave where it's woo. And I've almost never seen it look discontinuous. So I feel like using this Gaussian process model is probably good enough for the things that I've used or I've seen. So that would be my answer. Okay. I mean, your mileage may vary for the data that you have and the types of problems that you have. We'll see. So let me run some of this stuff. I want to show you how this executes as it goes. So I need to define some things. Where's Mars at? Mars, here we go. So I'll show you the code in just a second, and then I'll run it, and we can watch it as it executes. I also show you how the parallel processing works. So we've got about 10 minutes before the break. So let me just run through the code and the execution of it, and then we'll maybe look at it more when we come back. So what I'm going to do is create a workflow. I'm just going to add the Mars model to the Mars recipe. Now, like I mentioned, for some of these tuning parameter ranges, we've chosen ranges that are helpful, but maybe not the best. So number of components is really dependent on how many variables you're going to give to PCA. And so the default here for number of components is 0 to 4, I think. It's 1 to 4. And I think we could probably try more components than that. So what I'm going to do is I'm going to use the updating function that we talked about before. I'm going to create a parameter set from the workflow. It's going to have 3 things in it. It's going to have the product degree, which we don't need to change, 1 or 2. We're going to say generate Mars terms between 2 and 1,000. We don't try 1 because for the Earth package, 1 just means the intercept, and there's no, let's not even go there. So 2 would mean the intercept in one hinge function, and the largest number I would try would be 100. And then I'll set the number of components that go between 0, meaning skip PCA, or 20, which is use all potential principal components. So when it goes to do the search, these are like the bounds. So it might try like a 0 component model, and then it might bounce around and eventually come up against a 20 component model, and it knows not to do 21 or so on. So unlike grid search, it's not going to be generating a grid here. It's going to use these ranges to look at candidates and predict how well those candidates would work. So that's our parameter set. I'll answer the question in just a second. So what I'm going to do here is I'm going to submit this code in a second. Actually, so here's the code. We'll set the seed beforehand. I'll have it save the predictions like we did before. And verbose equal true, it'll print out some, it'll print out like how well it's doing at each iteration. By default, it'll minimize the RMSE, which is fine by me. And the default is also expected improvement with no trade-off, and that's good. Like TuneGrid, the syntax is very similar. We give it like our workflow in this case. We give it the resamples. We tell it how many iterations to go. It may end early if it doesn't find enough improvement. One difference is we don't give it a grid, but we give it our parameter set because we wanted to change the range of these parameters. I don't know why I did this, but for some reason I told it to only measure the RMSE. We could have it measure R squared also, which wouldn't be a big deal. And then the other thing of note here is, we don't have any data already. We haven't already done like grid search for Mars. We don't have any substrate for it to make the first Gaussian process. So since we have 3 tuning parameters, I'm going to tell it to generate 4 initial values. And what it does there, it does like a space filling design with 4 points. It resamples those, and then it builds like its iteration 1 is like the 5th model it tries. So the first iteration of the search is built upon the initial 4 in what we call like iteration 0. So it's 0 based, sorry. So I'm going to run this in a minute. I'm going to use multi-core and do that real quick. And then I'll run this and it'll show the logging, which I think is helpful to see how it's working. So it's generating the initial set of 4. Let me clear the log here because it's going to print out a lot. Let's see, if I look at CPU, it's running things on 8 cores for the first 4 models. So as it resamples them across all the time series resamples we have, it fit those 4 models. The best one out of the 4 had a RMSE of 1.8. It built the Gaussian model really quick. It generated predictions. Here's what it chose to try next. 19 PCA components, a second degree Mars model in 2 terms. When it does that, performance was awful. Like, this is really bad for these data. So it knows, well, that was a mistake. So it adds this 5th data point to the initial set of 4, and then it builds another Gaussian process model. It generates more candidates. Now it says, try 13 components with 8 terms and an additive model. Better, but not close to being optimal. And so you can see it's going and generating more stuff. On the 3rd iteration, it tried 20 components, additive model, and a lot of Mars terms. And that actually gave us the best results. So our previous best is 1.8. Now it's 1.2. And then it's just going to keep going. So it's going to try 100 with 1 component. One thing I've noticed about Bayesian optimization is it especially in the early phases, like, reduce your expectations of what this method does, like in the first 10 iterations. What I found it doing is it bounces up against the box. So if you have like 2 parameters and you define the range, it's like a box. And it'll start off and it'll go to one extreme in one parameter, and then its next candidate goes to the other extreme. And it's like it's trying to find the boundaries first to figure out like how bad that could be. And then it maybe starts looking in a more internal space. That probably isn't always going to happen, but I've observed that a lot when I've kicked this around. So anyway, so it kept going, tried a bunch of stuff. At iteration 7, instead of the best being 1.2, it got down to 1.13. And then it kept going. So that was at iteration 7. It keeps going and going. I told it to do 25 iterations. It's not, it's getting close, but it's not finding better results. And then once it gets to iteration 17, it tries again. And then by default, it says if you haven't seen an improvement in 10 iterations, it stops. So the best thing it came up with was iteration 7. And it would, when you do show best and all that, it would rank that one highest because it has the smallest RMSE. And you can see, well, you can't see it right now, but each individual model fit, when it generated the RMSE, that was all done in parallel, but all the in-between stuff can't be done in parallel. So yeah. One other thing to mention about this is you may have noticed that it says like generating, 2,935 candidates, and then it says generating this many candidates, and so on. So what it does is, by default, it generates a random set of 5,000 candidates, or it tries to. But in some cases, like with this model, all of our tuning parameters are integers. So we have product degree, which has 2 values. We have number of components, which has 21 values. And then you have number of terms, which has 99 values. And if you multiply that together, the total number of potential unique values is upwards of about 29,000 or 2,900 something. So you can see the number of candidate values is going down because as it generates more, there's only a unique number that you could actually use. So if we had like a real number in there, like penalty or mixture, this number of candidates would always be around 5,000 because there's infinite number of those combinations. But in this case, we have integers, and there's, if you sampled it down enough, it would eventually stop and say, I don't have any other candidates I could test, if you had a very small number of values. One other thing I would do real quick is I'm going to kill this and start it again. So we'll watch it run. Same seeds, it's going to give us the same results. I just want to demonstrate something. That if you're doing this on a new data set, and you might start running it, and you can do it in parallel, and be like, oh, that's nice, it's running in parallel. And then, you get the first iteration, which should be any second now. And then it takes like an hour to get the next iteration, just because you have a lot of data or your computer's really slow or whatever. You might get kind of frustrated, but then, historically you're like, oh man, if I stop now, I'm going to lose all this information. So the cool thing now is like, if you stop, if you hit escape, what it will do is it will return everything up to that point. So it says returning current results. It will give you the initial results plus the first 4 or 3 iterations that it completed. So you can stop it prematurely and not lose anything, which is a nice feature. Another feature that I'm not going to demonstrate is the control function also has a time limit. This is not perfect. We're going to work on this a little bit, but if you tell it to do as much as it can do in an hour, it'll stop on its own once an hour has been gone through. So yeah, those are the main things I can think about it before we move on. So we have a few minutes. I'll just answer questions until 3. Out of curiosity, how is TuneBase implemented? Is it pure iterative R code, or does the fitting get handed off to Stan, for example? Well, the code's on GitHub, if you're interested in seeing the code. What it does is, I looked at a bunch of packages to do Gaussian processing. I like Stan. Don't get me wrong. I like Stan. It's not known for its efficiency. And so I looked at using Stan for Gaussian processes. They have some code. It's not really standardized. It's not very, I don't say it's not production ready, but it's in little pieces here and there. So it's not like RStan where they have like generalized linear models ready and running and things like that. So I want to try Stan. I don't think it's going to be very efficient. But there's no like dedicated real production crayon Stan code to do Gaussian processes, unless that's changed very recently. I'm not really willing to write my own. These models take a lot of like numerical tuning and optimization to run efficiently, and that's not my wheelhouse. So if somebody has like a Stan implementation, I'd be happy to try it. But until then, so we use a package called, I think it's called GPFit. GPFit. It's been around for a while. Some of the maintainers are like old school like S and R people. So looking through it, I've yet to find like a serious problem with it. So there are a lot of them out there. So if you like search CRAN for Gaussian processes, there's probably, I'd say, like 5 or 6 different packages, and I looked through them all in terms of efficiency and some of the features and how easy it was for them to use. And this is the one that I felt did pretty well. So I'm pretty happy with it. This, I believe, let me check, but I believe GPFit passes the calculations up, to C. So let's look real quick. Oh, needs compilation? No. So it looks like it's a pure R implementation. So yeah, that's surprising. But yeah, that's what it uses. I thought it was using C. Anyway, if there's a better alternative, I'd love to see it. We're not necessarily married to it. But right now, this is the best one I could find. How does it work on categorical tuning parameters, making dummies versus parameters? Yeah, so it makes dummy variables and then puts them in the model. A lot of the Gaussian process models need you to put the predictors on the same scale. And this one in particular wants you to rescale them to be between 0 and 1. So if I have like the number of components, even though it goes from 0 to 20, when I hand that off to the GP model, I have to rescale that by the parameter range, not the data range, but the parameter range to be between 0 and 1. And so for example, if I wanted to optimize the in a k-nearest neighbor model, if I try to optimize the weighting function, like we looked at yesterday, it would create dummy variables for the ones that we've put in the model and then build the Gaussian process model on that. So that's the way that people typically do it. Yeah. Let's see, what's another question? Right, so there's the code. Somebody posted the code. Stan might actually be overkill for this application since we'll update the entire covariance function and you only use the mean and the diagonal of the covariance. Yeah, very true. So, yeah, I mean, in a way I'm a fan of Stan, but I have to admit, depending on Stan as a package maintainer is a painful existence. I've kind of told them that it's a lot, just to be honest with you. Just, compiling Stan quite a bit. We have some like Amazon instances where, they have very like not a lot of memory on them. We can't even load our Stan ARM on some instances. It takes up a lot of memory just loading the package, and just the amount of C code in those packages is very, very large and kind of unwieldy. I like it as a tool. And that's what I almost always use for Bayesian stuff, but it can be a little frustrating. Where are multiple cores being used, and when is it running one iteration at a time, potential splits? So what it does is when it goes to generate the initial set, it's running the initial set in parallel. So again, it parallelizes over the resampling method. For the Gaussian process, there's no parallelism there. And then, once you get a new parameter combination that you want to evaluate to get the resampling results, it parallel processes those. So it does like parallel batch, get a new combination, parallel batch of one, new combination, parallel batch of one. So that's how it uses parallel processing. There are other variations of this that have been implemented in Python, things like that, where, we could score like 5 models if we wanted to at a time, based on the Gaussian process and parallel process those. There's some things like that. There's also some other improvements that, depending on like how useful they might be, would be good ideas. Mars also, for example, has this submodel trick. So if you fit a Mars model with 20 terms, it's pretty efficient to get predictions on terms less than 20. You don't have to keep refitting the model. So for something like Bayesian optimization, I've thought about like detecting that and then doing like a line of, more than one predicted model, because we already have that model object. We can get very fast results. So like for this model, for well, not this one, let me look at a different one. Let me look at this model. For an additive Mars model with 20 components, we fit the actual Mars model with 57 terms, but we could very quickly get predictions on 56, 55, all the way down to 2. So that might be like a very efficient, it's related to like what they would call beam search in old school methods, but that might be an improvement that would allow us to do that when a model has the ability to do that. I think it would be more efficient and you get a lot of data very quickly. So there's a lot of, this has been a hot research topic for a while. So there's potentially a lot we could do here with it. And the last thing I'll show before Amada kicks us out is what we could have done when we fit this model is, for the initial here, I said, give me four space filling design with 4 values in the grid. Let's suppose I've already done grid search on a Mars model with the same parameters, like the same parameter set and all that. If I had that grid search object that came out of TuneGrid, what I could do is I could actually give it that to this initial. So give that whole object to the initial parameter here. And instead of it using like a random 4, it would build the Gaussian process model on the existing grid that you've already run, and then start to acquire new data points that are not necessarily on that grid. So if you want to, and this was brought up yesterday, I think, you can do like an initial grid search, and if you don't think that did well, or if you think you could like fine tune it a little bit more, you might feed that grid search into TuneBase and then see if it could take the existing best and just sort of riff off of that to get better results. So yeah, so that's we're not done talking about this, but we'll stop there because we have to take a break and switch sessions. So we'll stop here. When we come back, let's say 20 minutes. So let's say like 25 after, if that's cool. Because we want to make sure we get to the classification bits. We'll stop here and come back at 25 after 3. Make sure you go to the 3 p.m. session, and we'll start back up there. And any questions you have, just keep seeding the channel, and I'll answer them as they come in. All right. Looks like people are back. So we ran this code. Iteratively went through and tried to optimize things. And so, here's like when you log, here's the results, what it looks like. There are some nice autoplot methods. So if you run autoplot on that, there's a couple of different things it'll produce. So type equal performance will show you it over iterations. So here are the 4 initials. It did one initial that was a really awful model fit, and then you can see it started to slink down to very much lower areas of RMSE. It explores a little bit, so like it deviates from like what it felt was optimal at the time, and then slowly moves around and finds something good, and then starts to deviate some more. So yeah. So there's that. There's another autoplot method that's called marginals, which says just show me the distribution of the parameters versus RMSE. So you can see, not much of a difference between additive model and a model with paired hinge functions. It did not like it with 2 Mars terms. That was really underfit. And you can see as it adds more Mars terms, the performance gets better. Number of components, I wouldn't say that so far matters a lot. No PCA did about as good as PCA with 1 component, so maybe that's not that critical of a choice. And then you can also see how it changed over time. So you can see as iterations proceeded, it kind of bounces back between additive and not additive models. The number of components is slowly being driven down, maybe down towards 0 if we let it go a little bit further. That doesn't necessarily mean anything because, all these iterations shouldn't be treated equally because some of them might not be good performance. So just because it seems like it's going down doesn't mean that that's necessarily where the optimal results are. But it's interesting to look at, see how it proceeded. And another thing I mentioned is, I mentioned that you could pass in the results of like TuneGrid to TuneBase and just have it keep going. Like I could take my TuneBase results and give it again to TuneBase and just restart the process where it left off if I wanted to do that. So you can iteratively sort of apply these tuning functions over and over again if you want. So just like before, collect metrics and show best work the same as they did before. The only real difference is now you get a .iter column that says what iteration that was. So show best says, well, the best one so far was 7 components for an additive model using quite a lot of Mars terms. So, if we wanted to go with that, we could do that. Performance there was 1.13, which is a little bit, slightly hairs better than the RMISI from Glimnet. You can look at the standard error on that and see that that difference is probably not real, or at least pronounced, let's say. So did this do a good idea, or did this do a good job? Would it had it done better with grid search? So one thing I did was I calculated how many possible submodels there are, and then what I decided to do was to not in the notes, but fit basically that grid. I got all night. So what I did is I fit like the complete census, like the complete set of all possible models. And then, it said, well, okay, well, if we'd done like this massive grid search, what does the performance look like? Like how good could it have been in this particular case? And how did our search, did it do something that was relatively awful? It probably, we don't guarantee that it found the best, but if you look at the distribution of all the submodels, the RMISI that we got was in like the 90th percentile. So, that's like a B plus, if not like a minus. It's an A in grad school, but yeah. So, I did that just to see as like a reference point, because this is an interesting situation where we can compute all possible results. So I did that. If I were to plot the previous results, here's the distribution of all possible results. You can see there's like clusters. There's some clusters that just do awful, and we managed to sample one of them. Then there's like a relatively mediocre data cluster here. There's a lot of submodels that give you performance about 1.8, which we did sample some of those. And then there's like a cluster of really, really good models that we did wind up in a bit, but maybe there's a hair better we could have done. So we're like in the 90th percentile on like 15, 17 plus 4, 21 model fits. Got us, pretty good performance. So that's a little bit reassuring. It's going to be weird for people watching these videos later to wonder why Max is just staring at the screen for some periods of time. It's because somebody's typing a question in Slack. Would there be any justification to using the 5 best from the optimization runners we did as an initial parameter set for another run, or would you just get no improvement? Well, if you're going to feed that back into a Bayesian optimization, I'd give it everything, because the quality of your genetic algorithm using the full set that you've generated would probably be better than the Gaussian process model. I'm sorry, I said genetic algorithm. I meant the Gaussian process model that you would get off of the best ones. So I probably would just give it everything. I don't I mean, it's possible. I mean, you could try it, but my intuition tells me you'd probably want to give it as much substrate as possible to get that Gaussian process model working well. Um, like it's not really ready yet, but the simulated annealing search that we have is a much more incremental search. So I mentioned that Bayesian optimization can bounce around a lot, um, and simulated annealing doesn't. It's very slow incremental process. It doesn't move outside of a large neighborhood, and so like you might give like simulating annealing the current results, and it would take the best one and start to meander away from that one a little bit. So that would be a different situation where what you need for a Bayesian optimization model versus something like simulated annealing would be a little bit different. It's worth maybe backing up and showing you this one link. This GitHub repo I made like a couple years ago, it does like if you want to see, like I made a little GIF of like for a support vector machine, how the Bayesian optimization works. So it might be worth like checking this out. It's linked in the notes, but you can see sometimes it hits the boundaries of these things. And then eventually, in this particular case, it starts in on what it thinks is the optimal region and then maybe deviates a little bit outside of that, but it bounces around in this particular case and then seems to get close to the optimum pretty quickly. Here, I'll give you a link to that, but it's in the notes. Anyway, and there are some slides in there on simulated annealing and some other things in case you want them. Anyway, so let's see, where are we at? So somebody asked questions about what do I think about all this. I think it's reasonable. It's really big in like deep learning, but the thing is, outside. The thing is, I'm trying to be pejorative or anything like that, but I do get a little bit frustrated because there's so much going on in deep learning that I think a lot of people in that research field feel that everybody else's problems are solved by their methodology. So the things about deep learning models are they're mostly used for images, whether it's movies or images and text. And the thing is, the qualities of those two domains are that you usually have a massive amount of data and that you also have that data measured without much error, right? So if somebody types something, there's really no error in what they were typing. Or if you get an image, there might be some fuzz or something in it, but it's for the most part measured without error. And so I think a lot of times the conclusions that they come to are somewhat specific to their domain. My dog's unhappy, sorry. And so like if you work, like I used to work in drug discovery, and for the most part, there's not a lot of correlation between those predictors. And the jobs I used to have doing a lot of machine learning were in the complete opposite, where we have a good amount of data, but not terabytes of data or petabytes of data. A lot of what we had was measured with noise, and we had a lot of correlation between predictors. So the types of models and how they're operating are I think are much different. I think that what we find in deep learning can solve 20% of the world's problems. So I don't know that they're is terribly applicable outside of the situations where they've mostly been applied. So anyway, so I think the situations outside of deep learning, we have fewer like super critical parameters, like tuning parameters. So, a lot of these parameters have plateaus. So, it's not that hard to find, just by random sampling, a value on that plateau that does well. We can exploit parallel processing a lot more than they can because they tend to run on one big validation set. And so they can parallel process at the individual model level, but they don't really resample much like you would have to do with smaller data sets. So we have the ability to parallelize in some circumstances more than they do. And I think we have more well-defined ranges of tuning parameters. So I think they're somewhat different. So I have no beef with like the way they do things and things like that. But I think a lot of the Bayesian optimization literature is so focused on deep learning and the peculiarities of that, or the specificity of those types of problems that, it may not generalize as much. So, I don't think it's a bad way of going at all. I mean, at all. But, is that always going to be grid search? It might for deep learning models because they can't exploit a lot of the things that we can. And I don't know, there was a paper like a long time ago called The Illusion of Classifier Improvements or something like that. It was David Hand wrote this paper. And he was basically saying that, like, every paper you read in the literature shows that their method is uniformly the best for everything they tried. And, and what happens is when people publish things, they spend all their time, like years maybe, optimizing their method, and then they compare it against something else that they just tried a couple times and didn't really optimize. And so I think that when I read a lot of the things in deep learning literature and in other parts of literature, I think they don't necessarily consider the alternatives as strongly as they consider their own method. So as an example, I think space filling designs are a huge improvement on grid search. So I think you can get very, very good performance using space filling designs, way more than you could get with random designs or regular designs. So, I've yet to see like a really comprehensive evaluation between iterative search methods and really good and optimized grid search methods. So I tend to still want to do grid search more and more, but for the types of models that I fit, we're more optimized for those. So you can maybe make the argument that I haven't optimized the Bayesian stuff as much. So I would just say they're both work pretty well. So try them and see if what you find out, and if you want to, let us know. Could you use a space filling design followed by iterative search? Yes. So yeah, you could start off, we just did that, right? So when we generated those initial 4 parameters, that was with a space filling design. And so then proceeded with Bayesian optimization. So yeah, in fact, that's what I would recommend doing if you wanted to. Yeah. Yes, thank you for the classifier technology and the illusion of progress. It's oh wow, you have to find the archive package, or from archive. Yeah, it's an old paper, statistical science. This journal has it's got the two cultures paper. There's quite a few, even a statistical journal from, this is papers like 2006. Yeah, there's some good stuff in there. So, thank you. Very helpful. Okay. So then, what we can do is we can do the same thing we did as for grid search. Is we can do a collect predictions, do a join on our best results, and then do a ggplot. It kind of looks the same, or not that appreciably different than GlimNet. We still have these 2 data points that neither one predicted well. Again, one of these is because of the Trump rally. So it's not like we would be able to predict that well. It depends on your point of view, in which GlimNet would probably be easier to productionize compared to Mars. But, the quality of the model fits are not that different eyeball-wise. Yeah. And, from their metrics either. So let's say we select the best, which was, I think, iteration 7. 78 Mars terms, additive model, 7 components. So then this is where the finalized workflow comes through. Like, we don't have to prep the recipe or do anything. We just say finalize workflow. It inserts 7 in for the number of components in the recipe, 1 in for the product degree in the model, and 78 for the terms in the model. And then we have a single point of reference to fit this for the final training set. So this is nice. We just do this, and we're ready to productionize if we want. So that's very nice. Again, I mentioned Mars has variable importance scores, so we can use the VIP package for that. Now, we have our fitted model using Mars, I think I showed you this earlier, but I'll show it again, that there's this pool workflow fit, and that will pull out the fitted parsnip object. And then the VIP package works with that. We can look at the top 20, and then type equal GCV is what you would have to specify to get it to work with Mars. It says compute the importance using the GCV statistics. And you can see PCA1, very important. And then you can see the date fields are important after that. You do have more holidays that crop up compared to GlimNet. You have Thanksgiving, you have some temperature stuff, and so on. The one interesting thing is you can see I said 20 predictors, but then when we get down to like 19 and 20, there's zeros here. So if you look at it, only 18 model terms were used in the Mars model. Of course, the PC1 here is consisted of 20 columns of the original data set, but it shows, for example, the temperature and the minimum temperature that day were not used in Mars at all, so they have zero importance, and they're sort of functionally independent of the model fit, which is nice. All right, that's the last slide for regression. So before we jump over to classification, any other questions about regression, Mars, or GlimNet, or the Bayesian optimization parts? Okay. So we'll jump over to part 6 now. And that's classification. So we'll spend a little time, we didn't really spend much time with regression talking about how to measure performance. There's a lot more options for classification, so we'll spend a little time up front just talking about how we should fit our models. Why is this not incrementing? There we go. Talk about performance measures, the data set we'll use. It's probably a review for a lot of people. We'll look at classification trees and boosting, and hopefully we'll have time to go through naive Bayes. We are running a little late. There is a hands-on here that we'll skip over, if that's cool with everybody. So everybody take one data point from the test set and plot the variable influence on the predicted value, similar to LAM. Yes. So Dalek's package could do that. Let me look something up. So I've been talking to them about making sure that everything works with tidymodels, and I did mock up a gist for them to use. Where is that? So a gist in GitHub is like a way to have like a little static piece of code that you can share with people. So I'll put it in the notes here. It's an example. Actually, I think it uses the Chicago data we just looked at. So this uses like, I think, partial least squares. And then it fits the model. And then at the end, it does a bunch of Dalek stuff. It does the variable importance, and then it also does like the variable effect plots and things like that. So there's a couple notes in here like, hey, did this work right? But this is what I gave the package maintainer, really nice guy, to maybe as a substrate to make sure that everything works with tidymodels. Yeah. Okay. All right. So how do we measure performance? The thing is with classification models, there's actually two types of predictions that could be made. So here's an example data set that we have that has just some predictions from a test set. So the true value of our data, so in R, we tend to want classification outcomes be factors. So not 0, 1, not integers, not character. Most modeling methods want them as factors, and definitely tidymodels works with them being factor variables. And so when we build a model of whatever type, with data like this with two classes, there's two types of predictions we can make. We can make what we call hard class predictions, which is saying, I predict this is class 1 or class 2. It's like a discrete prediction. And then there's probability estimates. So most models, classification models, under the hood generate some numeric measure of it's not necessarily probability, but likelihood of being either class. So like if this were like a random forest model or something, this would be the class probability estimate. You might notice that these sum up to 1. And so these are sometimes called the soft predictions. I'll just call these the class probability estimates and the class predictions. So then different metrics can use different types of predictions. So we'll first talk about different metrics when you have a hard class prediction, and then talk about what you do to use the class probabilities. So, the simplest thing you can do when you have predictions on a data set is to do what's called a confusion matrix, which is like a fancy way of saying like observed versus predicted cross tabulation. So for this particular model, you can see that the truth is in the columns and the predictions are in the rows. So for example, there were 50 data points in the set where they were truly class 2, but they were predicted to be class 1, and so on. We have a plot method that does like mosaic plot. There's a couple different ways you could visualize these. The code here in Yardstick is we have a function called conf matrix, and then it takes the data frame with the data as the first argument. You'll see this a lot in these functions. The first argument's a data frame. The first arguments are not like vector. It being the tidyverse, we want to standardize on tables and data frames, and then you can give it unquoted names for the arguments that specify what the real value is and what the hard class prediction is. So similar to that is accuracy. So if we just pipe in the data set and then specify these columns, this looks familiar probably, I hope, to what we get when we had regression, where we have, we had like RMSE and things here. Now it has accuracy. It says estimator's binary. I'll talk a little bit about the estimator in a minute. And then here's the actual value of accuracy for this data. If there's a big class imbalance, you might want to use something like kappa, which you can do in tidymodels. Some of the estimators, as you'll see in a little bit, there are some type of metrics that are really specific to 2 classes, like sensitivity and specificity or recall and precision. If you have like 3 or 5 or 10 classes, there are ways to estimate those 2 class metrics like sensitivity or specificity using a different type of estimator. So they have like these combination methods like macro and micro. There's some notes at the very end on that. I'm not going to spend time on it now, but there are, in classification at least, there are a lot of different ways to estimate some of these statistics. So if you're wondering what binary means that I just took the standard, equation for accuracy when I had 2 classes, and that's what is here. So speaking of 2 classes, a little bit of a hubbub in the last, 20 years is over what do you do when you have 2 classes. This generates like 5 or 6 GitHub issues a year between Carrot and tidymodels. I think we've documented this really well, but it's maybe not be obvious. So, when you have 2 classes, you generally designate one as the event of interest, meaning usually it's the one that I'm most interested in. And so, that may not be a good thing, right? So if you're modeling survival, like death might be the event that you're interested in as opposed to living. So it's a subjective classification. It does matter though when you're going to talk about the different types of errors that you get. So when you have 2 classes, one common way of calculating errors would be sensitivity and specificity. So sensitivity would be of the things that are truly positive, what proportion of them did you get right? So if you take class 1, let's say, as your event level, the sensitivity would be 227 divided by the sum of 227 and 31, which is about 88%. And so that's related to true positive rate. So if my true positives, the things I know are positives, I get 88% of them right. And then specificity is more related to false positive rate. So what specificity would do is it would take 192 and divide it by the sum of these numbers. In this case, sensitivity is 79%. The false positive rate is 1 minus specificity. So we have about a 21% false positive rate. So sensitivity equal to the true positive rate, specificity equal one minus the false positive rate. So that's one way of looking at it. So the thing is, over time, a lot of people, so I'm not going to like history lesson like when I was a kid, but like when we think about what software was doing back when the S language was first created, I think they were less free in terms of how they would store their data because there was so much less memory on computers. So what happened was, I think originally people started to store their binary data like class 1, class 2 is 0 and 1. And so then if you think about what the event is, it's probably a 1. And so what you get is across a bunch of different R packages, you have some of them that just intuitively think that the second level of a factor should be the event because they're going off of that old binary encoding because 1 was always a second level of the factor, so we should just use that. But now that we have factors, it's kind of hard for me to conceptualize that the second level of the factor would be the important one. So so we have to set some standard, whether you're using MLR, or Caret, or tidymodels, as to what your convention is for what the event of interest would be when you have two factors. And so in tidymodels, you can change this, but in tidymodels, our convention is the first level of the factor is the event of interest. Now your calculations wouldn't be wrong per se, but it's just making sure you interpret things right. So if you mean your second class to be the event of interest and you do these calculations, it just means that your sensitivity and specificity are switched, which is an important thing to make sure that those are right. But in previous versions of Yardstick, when you started out, it gives you a message saying, hey, we believe that the first level of the factor is the important one. So, you can change it using, this and that. And so we still do that right now. But there are methods to change it back to using class 2 as the event of interest. So you just set that basically and then go on your way and everything works out correctly. But there's like almost like a religious war over this. And I've been fighting it for quite a long time. So, yeah. All right. So there's functions that compute the sensitivity and specificity called, actually, we did maybe update this. People rightfully said, you have these things that are called sense and spec, but maybe you should use sensitivity. So we have both them being listed as sense and sensitivity. And I think we'll eventually get rid of sense and go straight to this. Because it's, we'd rather have the full name just so you're more explicit. So you can use either these or their full names right now. The thing I want to say about this is because I used to work in diagnostics for a long time, like infectious disease diagnostics, is sensitivity and specificity to the things that people tend to measure. They're not necessarily like what somebody necessarily cares about. Like the sensitivity is, given that your result is an event, what's the probability that you predict it to be an event, right? And baked into that is this conditional that you know what the answer is. How well did you get the answer? It's not what people necessarily care about. What they care about is sort of the reverse of that. What they care about is, given that let's say my model said I'm an event, what's the probability that I truly am an event? And that's more of a Bayesian interpretation. So sensitivity and specificity are conditional measures. And just beware that they may not line up to what your expectations would be if you were using this model. So if you wanted to get the reverse, where you said, okay, given that I get an event from my model, what's the probability of it actually being an event? That probability actually involves the baseline prevalence of that event. So for example, if you're doing like COVID testing right now, let's say depends on where you are and things like that, but let's say the baseline rate when people are tested is like a 4% positive rate. Well, the probability that you truly have COVID depends on that rate, let alone what the model or what the diagnostic would give you. So we have these things called positive predictive values and negative predictive values. And those are sort of like the Bayesian analogs of sensitivity and specificity. Those are the things that tell you the thing that you really want to know. Like, what's a probability that I'm truly a positive given that my test said I'm a positive? And what sensitivity and specificity give you are the opposite of that. So anyway, that's just something to be aware of. Also, information retrieval tends to rely more on something called precision and recall, so you can still use those in tidymodels. That's all there. The thing is, on like most metrics, like I mentioned, like we can get class probability estimates, and then we convert those to hard class probabilities or class predictions. And so, the basic thing when you have two classes is putting like a 50% event rate on it. So, something that is above 50% for class 1 would be considered class 1. Otherwise, like in this case, it's class 2. So, but then the question is 50% the right cutoff? Because in some cases, like I work very close to where we make most of the world's, or most of the U.S., all the U.S.'s nuclear submarines. And a lot of the engineers I work or talk to and know who work there, if they're building a model or doing something to detect like defects in a screw or something that's going to get put into a sub, they want their like threshold for calling something to be a defect to be different than 50%. They would rather have more false positives and throw things out than false negatives where you get a bad screw and that could potentially like break. And so the question is, whenever you have two classes, is, well, wait, what was the threshold that I used to make the hard class predictions, and was that appropriate? And so that leads us to something like, what happens if we were to change that cut point? So, if 50% is the cut point, if my probability of being class 1 is greater than 50%, then we're going to say it's class 1. So what would happen if I raise the cutoff, let's say? So if the cutoff gets higher, what you're saying is the probability of class 1 has to be much more stringent for me to call it class 1. So what happens is you call overall less events. Since the true positive rate is related to events, the sensitivity tends to go down because you're just calling less things events. And some of those things are truly events. So the true positive rate goes down. Now, conversely, the specificity goes up because you're calling less things events. There's just a general improvement in the false positive rate. So the false positive rate goes down, which means specificity goes up. So as you raise the threshold for calling something an event, sensitivity goes down and specificity goes up because you're calling overall less than events. Now, if you decrease the cutoff and you make it easier to call something an event, the opposite happens. Your specificity gets worse because since you're calling more things events, that means more false positives. But on the true positive side, since you're calling more things events, you're catching more true positives. So the thing is, modulating this event will change the trade-off you're making between the different types of errors, like false positives and false negatives. And sometimes you might change the event rate, you might change the probability cutoff, and sensitivity changes a little bit, but specificity changes a lot. And so they don't necessarily change at the same rate, depending on the data set and the situation. So there might be some really good trade-offs you could make, depending on your problem, to optimize your cutoff. So if you didn't want to use the 50% cutoff, what would you do? And so the answer to that, the tool that was originally designed to sort of answer that question is something called the receiver operating characteristic curve, or the ROC curve. And what that does is, over many alternate cutoffs of the probabilities, it calculates the sensitivity and specificity over these different values. And then it plots them against each other. It plots on the y-axis a true positive rate, and on the x-axis, it plots 1 minus the specificity, which is the false positive rate. So let's maybe look at that plot and see what it looks like. So to generate it in R, at least in Yardstick, you give it the data, you give it the true value because it needs to know what that is, and then you give it the class probability column corresponding to the event, which, if we use the first class, is class 1. So if you compute the actual curve and plot it using the autoplot method, you get something that looks like this. So what this says is, if I have, so this is a false positive rate. If I have 0 false positives, as I change my cut point, sensitivity is getting better, but eventually as you get to this apex of the curve, now you're making the trade-off between sensitivity and specificity. So up here, as the false positive rate gets worse, you see it's going to the right, it's increasing, the sensitivity is actually getting better too, right? So the 50% cut point is probably going to be in here somewhere, where it's some sort of trade-off between sensitivity and specificity. But if you're more interested in finding the events like defects, you may want to choose a cut point that's closer here because the sensitivity is higher and you're willing to accept false positives. In fact, this is what you do with like COVID tests or screening, screening tests. Like you would rather accidentally call somebody COVID and have them, for example, having to quarantine for a little bit versus them going to church, let's say, and infecting a bunch of people. So it's like a good example of how you might choose to make trade-offs between true positives and false positives. So you usually calculate this over all possible cutoffs. And then since things are between 0 and 1 on both axes, like what would you have if you had a perfect model? If you have a perfect model, the curve would come up all the way up to 1, and then it would come directly over. So if you had data that was completely separable by a predictor, your RC curve would just hug this left-hand axis, and when it got to the top, it would hug the top here and go over. So if we wanted to come up with a single measure of how good my test is over like a multitude of cutoffs, what people typically do is they calculate the area under the RC curve. And again, since both these things go between 0 and 1, the best RC AUC you can get is 1. So as we get if we have this is actually pretty good. It's 0.939, basically 0.94. That, is fairly close, relatively speaking, to 1 compared to other models. Now let's say we had a model that we built that was on a bunch of just completely useless predictors that had nothing to do with the thing we're trying to predict. What would that curve look like? Well, in that case, if it's a completely irrelevant model, it wouldn't matter what the cut point is. So, since there's no signal there, it turns out that you would have about the same sensitivity and specificity regardless of the cutoff. So in that particular case, it would hug this sort of diagonal line and go all the way up here. And so the area under the curve for that is 0.5. So we typically think of 0.5 as like a model that's really not good at all. And then area under the curve about 1 is a model that it's nearly perfect. So RSC AUC gives us the area under the RC curve, and then RC curve gives us the data to plot on a curve, and autoplot can be used. So then there's a question, what is theme here? Sorry, that is, I believe, in the code. We have like a non-white background here. So this theme basically creates the background so it matches a slide background. And I think it is in the notes at the top. So theme is here. So it's in the notes. I just didn't show it in the slides. It's like the first thing in the notes. So, here's the obligatory GG animate GIF where you can see the threshold is changing. So as the threshold is low up here, we're calling fewer things negatives. Let's see. Wait, did I get that right? My son is on the other side of the room over here trying to distract me for some reason. And I wish he would stop. So anyways, the threshold is very large. You're down in this region where you're calling fewer things events. So sensitivity sort of takes a dive here. But on this part of the axis, you're calling almost nothing events. And there you go. Specificity looks much better on this side of the curve. So you can see how this changes as we adjust it. Okay. All right, so what are the good and bad about the RC curve? I think they're excellent. There's been, in the last 5 years, a lot of people that have been hostile to this approach. The nice thing about this is if you want to optimize sensitivity and specificity of your model, you might be optimizing something for the wrong cutoff. So the nice thing about the RC curve is you can get a measure of performance that is independent of the cutoff. And so what you can do is if you optimize your models on the area of the curve, you can sort of defer that cut point determination till the very end, which is a nice thing. You just don't have to worry about it until then. The other nice thing is it's robust to class imbalances. So sensitivity and specificity and accuracy are not. So if I told you, for example, that my model is 99% accurate and didn't tell you anything else, you might think like, wow, that's really great. But what if I told you there was like a 1% event rate? Then it is literally the most uninformative model possible because you can basically predict everything to be a not event and get 99% accuracy. So in that sense, like sensitivity, specificity, and accuracy are very sensitive to what the event rate is, whereas the ROC curve is not. So this is a good metric that you could use whether you have a 50-50 rate or a 99-to-1 rate. It works pretty well. So I tend to optimize on this quite a bit. I know that other people don't, but I find it to be good. In Yardstick, we also have multi-class versions of it. So if you have 3 classes, there are papers and things like that to show how to calculate an RC curve. So if you see like the estimator bit, like there is like the standard estimate when you have 2 classes, but there are alternate estimates you can get when you have more than 2 classes. And that's documented on the Yardstick website pretty well. Can I explain AIC? AIC is really very different than this. AIC is called the Akiki information criteria. Information criteria are sort of old, it's going to sound demeaning, they're very old school methods of computing performance. And what AIC does is it's a little bit like the penalization methods we talked about before, meaning that that if you like do linear regression and you calculate the sums of squared error, you could just keep adding predictors, and if you repredict the training set, your sums of squared error are guaranteed to go down, irregardless of how good those predictors are, right? It will never get worse when you're repredicting the training set. So AIC is a penalization method that penalizes your likelihood, which for linear regression is the same thing as the sum of squared error. And it penalizes by the number of parameters in the model modulated by the number of data points. So it's only applicable when you're repredicting the training set. And we don't really talk about it that much because we don't really believe in repredicting the training set. It also doesn't really help you in machine learning in some other areas because, like, what's the degrees of freedom of a GlimNet model, right? So you might regularize a model and it still might use like 100 parameters, but some of those you've made so close to 0, are they really parameters? Or like if you start off with 100 predictors, but the lasso eliminates some, I'm not sure I know what the number, like what the degrees of freedom are. So if you fit like a classification tree, there's no notion of parameters there. So, you know, in those instances, it's very hard to use them outside of a very classical set of models, and only when those models are generated, performance is generated on the training set. And again, we think that's a really bad idea. So, I mean, I'm not like, they've been very useful for a lot of things. On the Bayesian side, they use them a lot to compare models and things like that. I guess I'm not really saying you shouldn't do that, but I'm just saying for a broader set of models and a broader set of applications, they're not really applicable. So there you go. Okay, so let's talk about the example data. We're going to use a relatively small data set. It's a data set I worked on a long time ago where we were trying to take protein measurements from patients and see if we can classify them based on their cognitive ability. So this is like a big consortium we worked with where we had clinical data on mostly older people. And some of those people had very well characterized cognitive problems like Alzheimer's disease. And then we had a control cohort there were people who were not young. They were just people of about the same demographics that did not have similar cognitive problems. And so a bunch of things were measured. Some of them were really well known, like this thing called tau or amyloid beta. So we measured like a host of measurements based on laboratory tests. We had their age and sex. And then we also had their genetic makeup. There's this thing called apolipoprotein E, or ApoE is what we call it. And I'll call that genotype in the data. There's 3 main genotypes you could have, and you get one from each of your parents. So E2, E3, and E4 are categories of these genotypes. E2 is the one you want because very few people with E2 end up developing Alzheimer's. So in the data, the way that they're encoded are things like E2, 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 E3. And so something like E2, E2 means both of your parents gave you the E2 gene, or the E2 version of ApoE. If you were like E3, E4, that means one of your parents gave you A3 and the other gave you A4. And so that we know historically has been a good risk factor for things like dementia or Alzheimer's. So that's an important qualitative feature of the data. So almost all the predictors here are numeric, the exception of, well, sex has already been made into a dummy variable, but the main categorical predictor is the genotype. This was intended to be a feasibility study to understand if these laboratory tests that we were looking at had any sort of discriminative ability. So, the thing I caution people against is that, a small study like this is something, unfortunately, and it happened with this one, the media gets a hold of and say, like, we found the gene that can predict Alzheimer's. And it's like, well, no, like we didn't. We did a feasibility study on a small set of patients, and, we found this and that. So, when you're doing development of like diagnostics or drugs and things like this, we normally would have a sequence of many phases of studies of many patients so that each one validates the results of the one before them. I think in generally speaking, the public thinks that like you did one data set and you found the answer and that, we've cured cancer and things like that. So I do get frustrated that, in fact, with this particular study, there were some publications that were like, oh, they figured all this out. And it's like, well, no, this, we'd have to replicate this and so on. I should also say that even though tau and beta amyloid are important predictors of cognitive ability, every single drug that used amyloid beta and things that are very similar to amyloid beta failed in the clinic. So it's a good case study of something being important may not be helpful. Anyway, so what we're going to do is we're going to try to predict people's cognitive ability based on these measurements, whether they're the numeric protein measurements, their demographic measurements, or their genetic makeup. The numeric measurements have already been transformed, so they've already received what's called a Box-Cox transformation. So when you look at age, the units are not like 70, 80; they're in different units. And this is the data set we typically did our analysis on. So it's the one I included. All right. So it's in the model data package. So when you load tidymodels, you get that package. And if you just do data AD, you'll see what the ratio is. They're mostly control patients. There were 91, impaired, which is a little bit of a class imbalance, but not really hurting us too much. We're going to do a 90-10 split. We don't have a lot of data, so I'd rather include a lot of it in the training set and have the test set be sort of a gross measure of performance. So we'll rely a lot more on the training set statistics than we will the testing set statistics. There is like a gross double check of performance. So that's kind of the trade-off we made here. So because we don't have a lot of data, I'm going to do repeats of cross-validation. I probably in practice and probably back when I did this analysis, I probably used a lot more than 3 repeats, but I didn't want us to take all day computing this stuff. So it'll be averaging 30, let's say, areas under the RC curve than 10. The other notable thing here is we do a stratified cross-validation. So within each split, each of the 30 splits, when it goes to allocate the data into folds, it also uses the outcome to do that. So we made sure that the assessment sets have the same class frequencies as the analysis set, the same proportion of impaired and non-impaired people. So there's very little downside to doing that, and that's what we're going to do in this particular case. All right. Any questions before I go on? All right. So many of you have probably heard of classification trees. What they do is they search. This is going to sound a little bit like Mars, and they're somewhat connected. What classification trees do is they search through all the predictors and all the values of the predictors until they find a split of one predictor. So we might take a split of, let's say, age for these data, and that if it selects age of a certain value, the sort of method it uses to create that split, it says, well, if I use a split to partition my data into two groups, they don't need to be equal sized, but I'm going to, like on one side of the split, partition them and then have another side of the split. It tries to find the split that best isolates one class. So the best possible split you could get in a tree is one where, let's say, all the impaired people are on one side of the split and all the control people are on another side. So the objective function that it uses is something called impurity. It tries to reduce the amount of impurity. It wants a very pure node, and a pure node would be everybody is the same class, versus an impure or a very impure node would be like 50-50 or something like that. So it's trying to basically like make splits of the data that when it partitions them, they're mostly the same class. And so in effect, what it's doing is, like if you had two predictors, it would be basically making, the first split would be taking that two-dimensional square and slicing it down either the x or the y axis. And then if it did another split, on each side of that, it would maybe split them in the other dimension. So it's basically partitioning our predictor space into rectangular sections, kind of like Mars did. Now the difference is, inside those rectangular spaces, it's only going to make one prediction. It's going to say you're impaired or you're not impaired. It's not going to like fit a model inside of that. So basically, once it does these splits, the resulting structures are called the nodes of the tree. So it'll make the first split on the data and then continue to do searching inside of each one of those splits to keep splitting sort of like in a recursive way. So you start off with one split and then you get this like this expanding tree structure of if-then statements. So for a terminal node, let's say you did 3 splits, you might split first on X, or let's say you do 2 splits, you might split first on X, and then within X greater than 1, you might split on another variable Y, and then within those splits, you would classify things as either one class or the other. And you can see the class or the splits don't have to be symmetric. You might do a bunch of splits on one side and then just one on the other side, depending on the data. So that's in effect like the prediction equation for trees are just a bunch of nested if-then statements. So if this were your model and you get a new sample, you look at its value of X, and if it's greater than 1, then you look at its value of Y, and based on that, you either use this assignment or this assignment of the class predictions. If you've ever heard of a rule is basically something that can take a tree and then just look at every path through that tree. So in this case, we have 3 terminal nodes, which means 3 nodes at the very end, and that means we would have 3 rules for the different distinct paths through the tree. So there's a bunch of different ways you can fit tree-based models. They vary by like how they do the search through the data, the criteria they use, like whether it's impurity or something else. Some of them can do just binary splits. Some of them can do like 3, 4, 5 splits. They handle missing data differently. The way they prune the data can be different. By far the most popular is CART, which stands for Classification Regression Trees. Outside the US, the second most popular is the C5 or C45 methods, which are pretty close to CART but have some important differences. We'll just focus on CART for now because that's what people mostly use. If you're interested in learning the other methods and what is in R, I would suggest looking at the CRAN task view. There's a heading for tree-based methods, and you can see what's there. So again, kind of like cart, what trees do is they start with a growing phase, where they start conducting these splits, and then recursively within each subject or subset, conducting these splits until they basically run out of data. So there's this parameter that we call min-n, and it means how much data do you need to have in a terminal node to keep splitting. So if min-n were 20, and your terminal node has like 5 data points on one side, it wouldn't have enough to keep splitting, so it would sort of stop there. So as min-n gets smaller, the complexity of the tree or the depth of the tree can change, can increase. So at each split, like I mentioned before, what it does is it tries to find the most pure nodes. So as an example, what I did is I balanced the data we have so it had like a 50-50 event rate. So here's an informative split for A beta. And the example here is one where on one side of the split, so it split on A beta value of 11.3. On this node, mostly the data is impaired. So it's a pretty pure node on this side. On this side, they're mostly controls. It's not as pure, but it's pretty good. So this is a relatively good split of the data. Whereas this one's not so much because everything's almost like 50-50 on either side. So there's not much informativeness in this split because the odds are about the same of whether you're impaired or not impaired, whether here you're getting a much more definitive look at the data within the terminal nodes. So just so you know what the method used for splitting, it's based on impurity of the resulting nodes. So cart initially does a growing phase where it goes to the deepest possible tree based on the parameters that you've given it. But there's this recognition that that probably overfits the data. So cart has this methodology that it does to find the right size tree. So what it does is it looks at the error rate over different depths of the tree. So if it has like 10 terminal nodes, it might compare that to a tree, the same tree with like 9 terminal nodes. And then what it can do is it can have a way of computing the error for both of those, and then it penalizes the error rate by the number of nodes. So this might look familiar in a way. It's very similar to the glibnet penalization, where this is almost like the penalty parameter, and then it penalizes by the number of nodes. So if it had 2 trees and they both had an error rate of, let's say, 10%, one had 20 nodes and the other had 2 nodes, this criteria would favor the one with 2 nodes because it has less of a penalty than the deeper tree. So very much like the glibnet model, it's trying to penalize complexity of the model. And also much like the glibnet model, and they were invented by some of the same people, the CP value, this complexity parameter, tends to give you values between 0 and 0.1. So a CP value of 0, generally speaking, gives you the deepest possible tree, which means it doesn't do really any pruning at all, because there's no penalty for the number of nodes, so it doesn't really prune at all. And the way they have things set up in software, a value of 0.1 almost always is what we call a stump, which is a single split of the data. So as CP gets lower, the model gets more complicated, and as CP gets closer to 0.1, it becomes very, very simple a lot of times. So how do you set CP? Well, you can do it manually, like we did with Mars. You can say, I want a complexity penalty of like, 0.001 or something like that. But if you don't want to do that, cart has an internal method, also like Mars, where it can find the right size tree based on its own internal cross-validation. I tend to set things manually. I think that the complexity of cart is underestimated by its internal cross-validation. So you could optimize it using tune, or you could let it do its own thing, depending on whether you tune the cost complexity parameter. One downside to this is what do you do about class imbalances? The thing is, the impurity measures are relatively resistant to the class imbalance. They're not perfect, but they're relatively resistant. But the problem is when it goes to prune the model, it uses the error rate, which is like 1 minus accuracy. So the pruning is negatively affected by an imbalance. So what you might find is it might trim like one part of the model because that's where the most data points are. Because if it splits and gets almost all the majority class on one side, that affects the error rate. So it would treat that node differently than it would treat a node with a smaller event rate. So it is a little bit sensitive when it prunes to class imbalances. So anyway, the two main tuning parameters we would do would be tune the cost complexity value and tune the minimum number of data points needed to do splits. And they both, in their own separate ways, control how deep the tree are. So you could have a cost complexity value of 0, which gives you the deepest tree, but if min n is set really high, that prevents a very deep tree from getting fit. So they're both different ways of modulating the depth of the tree. Cost complexity affects the depth after it's been grown, while min n affects the depth during the growing process. Okay. So what's good and bad about them? Well, the first thing is, how do we make class predictions? What we would do is we would look at the terminal nodes, and we would use the proportions of each class and terminal nodes to make predictions for the probabilities. The number of possible class probabilities are usually low. So if you have like 9 terminal nodes in your data, you only have 9 unique probability values. And that's an indication that it's not the most performant model. In theory, trees are interpretable if the number of terminal nodes is low. But if you have a lot of data, the trees can get very deep. And I think they're not really interpretable at that point because you have like 17 if-then statements you have to go through to understand them. They fit very quickly. So even though you're doing these exhaustive searches of the data, it goes very quickly. And they're also unstable. So what that means is if you change the data a little bit, like the training set a little bit, if that initial split changes from one variable to the other, then one variable to the other, all the splits below it change. So a little bit of difference in the data can make a really big difference in the tree. So the performance of the tree might be about the same, but which variables are split in which order and their split values might change quite a bit. So they're called, from a technical standpoint, they're called unstable models. They have high variance. The cool thing about them is they don't need really any pre-processing. You don't need to make dummy variables. They can internally impute missing data. Transformations aren't really needed. They're they're like the tardigrades of models. They'll take whatever you throw at them and be fine. They're low maintenance, basically. And also one cool thing is that they all automatically, like Mars, they conduct feature selection. So if you never split on a predictor, they're not part of the prediction equation and you don't really need them anymore. So you don't have to wrap like trees around some sort of fancy feature selection routine. It just happens as you build the model. The dog likes classification trees. The dog likes walks. And I shouldn't even say that word. She'll go ballistic in a second. So that's the groaning you hear behind me. And it's raining outside, so yeah. All right, so how do we fit them? If we want to rely on the internal cross-validation process, we just don't tune the cost complexity parameter. We can tune min n, and then it gives us what we get. If you want to set it and tune it externally using our own cross-validations, you can do that. So we can tune over this and this, set the mode to classification. And then the engine we would typically use is called rpart, recursive partitioning. And that's the best single tree package we have for this. Maybe unsurprisingly, I usually do this. So for our data, what we'll do is, we'll save the predictions. There's also an option to save the workflow at the end. So that was for some stuff in the extra slides. We're probably not going to get to those. You don't really have to worry about this too much. But saving the predictions like before, we'll save all the out of sample predictions. We can create our model just like I showed you. We can use a basic formula here. Again, you don't have to make a recipe for this. One important thing to know, and I already mentioned it, but it's worth emphasizing, is even though we're using the formula method, our part does not make dummy variables. So like if we have genotype, what it can do is say, well, if genotype is these three values versus those, those three values, here are my splits. So it can make like grouping splits on categorical predictors. It doesn't need to be like if E2, then this. It can treat the factor predictor as a factor. So even though we're using the formula method, most model functions would make dummy variables. Our part does not. And so we do not when our part's being used. So just an important note. So we're going to create a workflow, and then we're going to do a regular grid. We're going to do these cost complexity values and min n 5, 10, and 20. I think the default for cart is 20. So we're going to see if we can make the trees a little bit more deep than they would normally be. So again, we have a grid here, so we'll just put that inside of TuneGrid. We have our workflow, our resamples recreated. All this is pretty much the same. The metric, we'll just measure the area under the RC curve. If we didn't put this in here, it would measure the accuracy in the area under the RC curve. So we'll optimize everything and compute just the area under the RC curve. It runs really fast, even though we're doing a lot of fits. I'm kind of going a little faster through this so we can get to some of the other materials. And then show best, if we do that, it ranks them like it normally would do. In this case, it likes, not the deepest tree in a min n of 20. I think that's mostly because the amount of data in each analysis set is not large. So it's going to prefer, I think, simpler trees because it thinks otherwise it's overfitting. The area under the RC curve for that model is estimated to be about 0.814. Now you might notice that this is 30 now, since we did 3 repeats of 10-fold cross-validation. Instead of averaging 10 things, we're averaging 30 things, and that reduces the error of this considerably. So you can see also there's a lot of other models we could have chosen. So if we would prefer some of these others, they're really not that different than the one that we have. So that's good. Autoplot, when we do a regular grid, it gives us this nice little plot. So you can see we have very simple models. We don't get a very good area under the RC curve. As we increase the complexity, all the models improve. But if we allow the model to initially get too complex by having a node size of 5, you can see maybe it's overfitting a little bit and performance kind of drops off. It doesn't matter how much we try to change the pruning, the performance is about the same. And then you can see it definitely prefers to have less splits because it's generating less splits as the node size increases. So this particular data set, and especially the size of this data set, you get better performance when it has less complex tree structure, is the message you're getting from this. So, I mentioned that there's a lot of things here that look the same, and that's because they basically are the same. These values are just slightly different than each other. So I think it probably shows this one to be optimal, but anything from here all the way down would probably give you like the same model. So again, when I keep talking about these performance plateaus, it's not, these models are not the hardest thing to tune because at some point you get like performance being the same over a lot of the different tuning parameter values. And this is yet another example of that. Now this is a plot, right? So what we can do is we can extract the predictions. And for every one of the 30 resamples, we have all the different tuning parameter values. So we have a lot of curves here. So what I'm going to do is I'm going to filter the predictions down to the best that I chose. I can group by the resampling indicators. Since I'm doing repeated cross-validation, I have two IDs that define the repeats and the folds. So if I do a group by on that, I can compute the RSC curve for every assessment set. So at this point in my computations, I have 30 different RSC curves for 30 different assessment sets. And if I autoplot them, that just overlays them. So it respects the grouping of them. And, you can see the variation of these curves. The assessment sets are not very large. Here's one that's really not a very good measure of performance. Here's one where it is really good. There's a lot of variation here because none of them have much data in them. And so one thing we can do is plot the approximate curve. So we can kind of like average these curves in a way. So what we can do is we can pool all of the predictions that we have here and then create one RSC curve. And so this sort of approximates the average curve. So I wrote a little function that says, get my predictions, select the best one, and then instead of me doing a group by on ID and ID2, produce one RSC curve. I wouldn't normally say to do this, but it's better. The approximation may not be great, but it's better than looking at like 30 overlaid curves that have a lot of variation in them. So then I wrote another function that uses this one. What this does is we can give it a series of different tune objects. It'll compute this approximate curve for each one of them and basically overlay them using a ggplot. So all this function does is repeat that same process for every model that we give it. So as we calculate more models, we can give them to this approximate RC curve function. It'll just overlay them in a ggplot. So when we have one of them, we can say, give me the approximate RC curve, label it as cart using this object, and you can see that this is like the average RSC curve that we get. It also highlights the 50% cut point. So the default 50% cut point, since we have mostly non-events, tends to optimize on the false positive rate instead of the event rate associated with the events. And this is pretty typical. If you have like a 1% event rate, the default 0.5 cutoff is usually like way down here, which is another indication that it might be worth optimizing the choice of what the cut point is. So, our performance here is about 0.81. It's not horrible. It's definitely signal, but the question is, well, some of these protein biomarkers and things that we measured in genotype are important, but would another model give us better results? Like how much of this performance is based on the actual predictors and how much of it is based on the ability of the model to evaluate them? So we'll proceed to another model in just a minute, but before we do that, much like before, we can look at, we're going to skip this, we can look at variable importance. And it works kind of like Mars, is every time you do a split of the data, it catalogs how much impurity was resulted in that node. So it just accrues improvements to the model. If you split on the same predictor more than once, it just keeps adding importance to that particular predictor. Oops, this shouldn't be in there. That's from an old example. It doesn't apply. So what we can do like before is we could use the VIP package on the RPart model to figure out what was important and what was not. We'd have to like finalize the model, fit it using the training set, and then run VIP on it, just like we did with Mars. Thoughts on correlated variables and their impact on variable importance? Yes. Is there an effective way to resolve the correlated variables? Yes. Let me give you a link. What you could do is you could do with a recipe like a correlation filter up front and try to reduce the amount of correlation in the data before giving it to a tree. That's probably the best way of dealing with it. It's not perfect, but it's what we have. In one of our books, so what happens is, imagine you have like a really important predictor and you build a model on that, and its variable importance score says it's really important. If you just take a column and give it a different name but make a copy of that predictor, what happens in tree-based models and some other models is, if your importance score, when you just had one copy of the column in your data, might be like 80. The value might be like 80. It's like pretty important. But once you add another copy of that in, it does like a linear dilution. So it'll randomly pick between those two columns because they're the same data for which one to split in a tree. So what the result is when you measure importance, the importance would be like 40 because its original importance is split between these two variables. And so there's an example of that in one of our books. We show it for random forest, but the same thing is true for any tree-based method. So the thing about tree-based importance methods like random forest is if you have a high importance, you can feel that predictor is important. But if you have a predictor with low importance, you don't know that it's irrelevant because it might have been because it's correlated with something else. There's a real downside to some of these tree-based methods. So what you can do up front is you could do step core. So let me give you a link to that. Step core is a recipe step that will eliminate correlated predictors. So instead of using PCA, you could get rid of some of them up front. I didn't do that. So there's a link to that recipe step. So that's what I was just doing. Okay. So let's talk about boosting. Boosting was originally designed for two-class classification problems, and this original algorithm was called add-a-boost. And it's easy to introduce how boosting works based on this original implementation. It's not really what we do now, but it does kind of give you an example or give you a sense of how boosting works. So, let's say we fit our classification tree on our data, our training set, and let's say we repredict the training set. We know we shouldn't do that, but let's just say we repredicted the training set. Some of those training set points will get correctly predicted and others will not. And so the thing is about that first cart tree we generated, all the data points in the training set are treated equally. So what boosting does is it generates an initial tree using whatever tuning parameters you want to use. And it takes that initial tree, it repredicts the training set, and the ones that it predicted well get less weight in the data. So their sort of case weight gets decreased. And data points that were incorrectly predicted, I have this wrong in the notes. Samples that were predicted correctly have decreased weights. Oh, that's wrong. Sorry. I got to change that. Wow. So what it will do is it fits a second tree based on these new case weights. And what it's going to try to do is the weights that have been, or the samples that have been missed, it's going to work harder on the second tree to predict those well. And the samples that have been predicted well are going to be de-emphasized on the second fit. So what it does is it saves that first fit in like a measure of its quality, like its accuracy. The second fit in boosting is based on the first fit because it uses those case weights, but it's a slightly different tree because the case weights are different. And again, it tries harder to get the ones that it missed the first time. So then on the second fit, it further adjusts the case weights. So it'll take samples that were missed and will increase their case weight. So if I miss a sample twice in a row, its weights are getting higher and higher, but a sample that I get correctly twice in a row get lower and lower weights. And otherwise, they just bounce back and forth. And so what you do is you make these series of models that use the case weights from the models that came before them. And so it's always trying differently to better predict different data points in the training set. And so what you do is, let's say you do 100 iterations of that. At the end of the boosting process, you have an ensemble of 100 different trees. And so that sort of encapsulates what the model is. So what you do is when you go to make a prediction on a new sample, you would run that new sample through all 100 trees. Each tree would get like a vote for what the final prediction should be. And those votes are weighted by the quality of fit for each individual tree. So if we have like tree number 70 was like almost perfect accuracy, that would have more weight in the final prediction than tree 17 that had very low accuracy. So it takes this ensemble of things, of trees, it makes a prediction, like a weighted prediction, and that final prediction is like the ensemble prediction of that sample. So initially, under the hood, it makes 100 sub-predictions and then combines them into one final prediction. And it turns out that like the reason that this works pretty well is I mentioned trees are unstable. And that is a problem of variance, that predictions coming from a tree have high variance. And, as a statistician, like if I'm doing an analysis for somebody and their data is really noisy, like the typical thing I tell them to do is get more data, because you can drive down the noise by sampling more data. So what boosting does is it's trying to minimize the variation of prediction by giving you more of those models to combine. So by averaging models, many models, you're decreasing the variation of the final prediction. And the reason this works so well with trees is that trees are unstable. So this thing where we adjust the case weights, we can get vastly different trees from iteration to iteration. And that's important because if the trees didn't really change much as we increased or decreased their case weights, we'd be averaging like the same tree, and averaging the same number doesn't really change its variance. So boosting wouldn't really work that well with something like linear regression, because linear regression is not unstable like classification trees are. So boosting works mostly on unstable predictors that have high variance, and it mostly increases performance of these models by averaging out the model-to-model variation. So just as a sort of like demonstration of that, here's some data. I fit my initial model. Here's the card tree. Everything above this line here gets predicted as a bluish, greenish circle, and everything below is red. And then like this red data point gets a higher case weight in the next tree, whereas all the blue ones above the line get their case weights lowered, and so on. So when I go to fit the second tree, I change the size of the points based on their case weights. And so these small data points don't really matter so much, and the blue ones or the larger ones do. You can see that the tree fit is different than it was the first iteration, so I get a different tree. Now I have this data point up here. I've missed it now twice. Its case weight is going to get bigger. The data point here I keep getting right, so its case weight is going to get smaller. And then the ones that have been on the edge each time are going to have like differential case weights. So boosting iteration number 3 looks like this. It's trying really hard to get some of these data points because they have really high case weights. And there's some of them, it's not really going to try hard at all to get, because we keep getting them right. And so then the 4th iteration, you can see how it changes in the 5th iteration. So we're getting very, very different models because we're just adjusting up and down the case weights. And the differences in these models helps us average out the overall tree-to-tree differences and gives us better performance. So, I mentioned like back in the day, when boosting was introduced, the model that they used could only be run with 2 classes, and it could only, so it's only regression. It could only make, I think, class predictions, like hard class predictions. And so what happened is the statisticians started looking at this, and they realized a lot of the math looks a lot like things that they knew about, like gradient descent. And so they sort of adjusted how boosting works. And most modern boosting methods we use now are called stochastic gradient boosting, and they're kind of based on the statistical properties that, or the statistical bells and whistles that were added to the original model. And it also benefited from some of the deep learning research, because during deep learning, those model fits are very difficult to do. And so they did a lot of work on improving how gradient descent works. So the boosting models also benefited from a lot of the research that was done in deep learning. There's a lot of different boosting tools out there. The one that people use the most is something called extreme gradient boosting, which is called XGBoost. And that's the one that we're going to use here. Actually, I didn't update this slide either. Yikes. So we are going to use XGBoost in the notes. It does have a lot of tuning parameters, though. So, that's one downside to it. Despite that, it can be relatively easy to tune. There's a lot of plateaus in these parameters. And so it's even though there might be like 7 or 8 tuning parameters, they tend to be pretty easy to maximize. Some of them are related to how the tree is constructed. So we have the tree depth, where we can, instead of using cost complexity, it says, what do you want the depth of your tree to be? Min n is the same thing we had before, how many data points you need for splits. The loss reduction is very similar to min n. It's basically another control over how much splitting is done. One of the main tuning parameters here is trees, and trees is like how many iterations of boosting do I use. So typically, that can range from anywhere from 10 to thousands, depending on what your data set needs. Some other data tuning parameters that you could optimize are related to the optimization process. So the learning rate is basically something that the statistician suggested using. And what that is how fast you adjust these case weights. So if your learning rate is really high, that means that these case weights are very quickly changing between iterations. But if your learning rate is very low, that means the case weights sort of very incrementally change. And some data sets prefer fast learners, some data sets prefer slow learners. So it's definitely something that we should optimize. One other thing that you can optimize or not is this something called sample size. Like, remember I said that we know that repredicting the training set's bad. So what the statisticians also recommended is, in order to get those stage weights where we estimate how well the tree did, what we can do is we can do like we do with resampling, is at every iteration of boosting, we can leave a separate little data set out and then fit the model on this and then score the model on that. And that improves how that weighted averaging of trees occurs. So, I typically maybe set this sample size to, like 0.8 or something like that. And then try to optimize the model and see if XGBoost is even going to work well. And if it does, I might try to later on fine tune this to be optimal. Another thing you can do is you could set trees to be really high, but optimize and not tune it, and then optimize the stopping iterations. So XGBoost has a feature where if it doesn't see performance improve over like 10 iterations or something, you can have it stop training there. So you can do this like faster fitting. You don't do 1,000 trees and figure out what the number of iterations should be. You can optimize the stopping criteria. It's kind of the same, but optimizing sample size instead of trees could be faster to do. The other thing about this model that we should say is in fact, every other tree-based model I know of can handle predictors that are not or that stay as factors. So I mentioned cart, you don't have to create dummy variables. Random forest, C5, like all the other QBIS, all the other tree and rule-based models don't require you to make dummy variables. The implementation of XGBoost does. So it's like the counter example. So for like genotype, we'll have to make dummy variables out of the factor variable. So just keep that in mind. We've automated some of that. So if you make a mistake and don't create dummy variables, I think we do that for you behind the scenes. Let me real quick. I'm going to see if I can go over a little bit. What I'll probably do is I'll probably continue to go through all the slides, and you guys can head out if and when you need to head out. Because we're recording this, that means you can have access to all the materials and have me go through it, through the videos. You're welcome to stick around. I just asked how long I can go over inside of Hopin, but I'll definitely try to get through all the materials, whether you stick around or not. So if you need to head out or want to go to the other stuff related to the conference, go ahead and do that, and I will make sure the video gets posted. Okay. So here's what we'll do, is we will optimize trees, the min number of data points needed for a split. We'll also minimize the tree depth and the learning rate. We'll do that using, of course, XGBoost, and set the mode to be classification because that's what we're doing. The model here is called Boost Tree. So Boost Tree can do C5 and XGBoost and a bunch of other things. So we'll set the engine to be XGBoost. And then all we'll do is we'll update our cart workflow. So we'll keep everything the same except for just switch the model out with the boosted mod. Now that cart workflow doesn't make dummy variables. We have it set up to where we will for you if it hasn't been done. So anyway, so the tune grid bit kind of looks the same as it did before. The one thing we'll do is we'll use a space filling design to generate 20 different combinations of these 4 tuning parameters. So we'll just let, tidymodels knows what the range of these parameters are, and it will create a grid based on a space filling design. So, and again, we can run all this in parallel. When we do that, we can look at our approximate RC curve and overlay that with the cart model. And we can see that overwhelmingly the performance improves using boosting compared to cart. So we had about a RC value of 0.81. Now we're at about 0.9 based on our results. Show best says, it liked 300 trees, minimum number of samples being 8, a depth of 8, and a learning rate that was relatively fast. And then autoplot will help us understand what was important. XGBoost definitely did not like having larger node size like our part did. So, we can't go much further down than what we tested. We tested like 4 or 5. So, that there's probably not much we can do there. We might want to, on a second pass, increase the learning rate beyond what was sampled in our grid. It looks like, there's definitely an increasing trend here for learning rate, and then maybe raising the learning rate upper bound might be a good idea. We might be able to push into the 90s for the RC curve. And the tree depth didn't really seem to matter all that much. So it might make sense to take the best value here. Maybe we put this into the Bayesian optimization and let it do its thing for 5 or 10 iterations. But you can definitely see there's an improvement in performance by doing this. So we can select the best, finalize the workflow like we did with Mars, and fit it. So we don't have to worry about prep or juice or anything like that. And then we have our XGBoost model that if we wanted to predict the training or the test set now, we could do that. And again, much like the other things, we can get our variable importance scores from this fitted model. So if we look at the top 15 features, it liked tau the most. VEGF is another protein that it's not surprising that it's there. One thing I actually went back and made sure this wasn't an error. Genotype didn't show up here. I was very surprised by that. I did make sure that it was given to the model, so it's not a bug. It's just, for me, a little bit surprising that this particular model did not really use it very much. There is, I should say, XGBoost and CART have a bias in their splitting routines that the splits, you could have 2 different tree splits on two different variables that give you about the same performance. But if one has a lot of different unique values and another has a few different unique values, there's this bias where it will almost always favor the one with more splits or more potential values. So that's pretty well known about a lot of tree-based methods. That might be what's going on here because we only have 6 unique genotype values where we have, almost a complete unique tau value for each subject. So that might be the answer to that. All right, so this model is looking pretty good. So that might be a good solution to what we're doing. It gives us some sense of what these proteins, at least from machine learning perspective, are important. So that might help us out a little bit. So before I move on to naive Bayes, which is like the last section, is there any questions people want to ask? All right, we'll move on. So naive Bayes is based on this thing called Bayes rule, and you've probably heard about Bayes rule. I'm going to throw a little bit of math at you, but it's not going to be that bad. What Bayes rule does in the context of classification is it's trying to estimate this probability. And what this math says is, given, the bar means given I have the predictors that I have, like my genotype, my age, and things like that, what's the probability I'll be whatever class that I'm looking at? So given that, for example, I'm a guy who's about 50 and I have all these laboratory tests, what's the probability that I'm impaired or not impaired? So that's what we're trying to estimate. So it's like we're trying to do a good job of estimating the class probabilities. So what Bayes rule does is it decomposes that a little bit. It needs something called the prior. We'll talk about that in a minute. That gets multiplied by something called the likelihood. The likelihood I will go through in a lot of detail because that's where all the action is in Bayes rule. And then this is the probability of getting the predictor values that you had. So if being like a 50-year-old dude in this data set is somewhat extreme, this probability would be relatively low. And so, it decomposes in this prior likelihood evidence. And a lot of times, to be honest with you, as you'll see in a little bit, we don't even really need to compute the evidence in the context of classification models. You'll see how that works in a minute. So let's talk about the prior for a minute. The prior is like the baseline level of your outcome events in the wild. So like maybe forgetting about this data set, if I were an expert on cognition, I would say, well, in the general population, what's the average probability of having cognitive problems? So like you might say like within an age range of like, let's say people above like 60 or something like that, what's the probability that like a given person in the street is going to have cognitive issues? And so what that is it's your prior probability. It reflects your prior belief as to, independent of any predictors or anything, what the rate of the event is in your data set. So again, if we were thinking about COVID-19, I hate to keep talking about it, but the prior there would be like, what's the baseline infection rate across, let's say, people in the US? And so experts would probably be able to tell you, sometimes it's based on data, but they wouldn't necessarily be computing it from data automatically. They could, but they would say like, I think the baseline rate on average is like 3% or whatever they think it is. And so that's something typically we can compute from our training set, but in Bayesian models, you have the ability to modulate your prior belief, not modulate it to optimize your model, but modulate it based on what your experience is and what you think it should be in the data. Okay. So that's something you kind of set up front or estimate from your training set. So the action, as I said, is in this likelihood bit. So let's talk about that for a little bit. What that means is what is the probability that I get the predictors that I got given I know what the class is? So like I said, like I'm a 50-year-old guy. If those are only the two predictors in the model, what we would say is like, well, what does that distribution of those predictors look like for the people who are impaired? So given that they're impaired, what does my predictor distribution look like? And then you would have another distribution that says, well, given I am not impaired, what's the distribution of those parameters? And these things would be computed from the data. So the problem, though, is that even with something like age and sex, like you need to compute by default, that probability is like a joint probability. It's like a multi-dimensional probability. And so just computing that with those two predictors might actually be very hard to do. And so then, we have like 128, I think, laboratory measurements. We have genotype, we have a bunch of other stuff. It's very, very, very difficult to generate a probability in high dimensions of a distribution. So if we have a really multi-dimensional distribution, even if we have a lot of data, that's very difficult to do. So you might be wondering why it's called naive Bayes, and that's because to compute this quantity here, we're going to make an assumption that we know is probably not true. The assumption is that all the predictors in the data set are independent of one another. So for example, I think if you plot like tau versus A beta, you would see a correlation between those two things. So we're going to assume when we compute this probability that there's actually no correlation at all between them. And that is a false assumption, but it allows us to calculate this probability very efficiently, if at all. So the assumption is usually bogus, but it tends to be needed to compute the model. So here's an example. I simulated some multivariate normal data with a correlation that's not zero. So you can see, since it's like a pancake here, it's not a random jumble across the whole square. These are fairly highly correlated, and these lines here are like the estimated probability cutoff. So like this line here at the end would be like the 1% probability, like the 2% probability, and so on. So based on these, the probability of obtaining data points in the mainstream of this data are probably pretty high. But if we look at a data point like this red one that's on the off diagonal, there's a very, very, very low probability that we would observe this from a multivariate distribution like the one we're looking at. And since I simulated these data, I can actually calculate what this probability is. And under the correct assumption of correlation, that these things are correlated, the probability of getting this data point is extremely rare. It's a couple decimal places down the line. Now let's assume for a minute, like the naive Bayes model does, is that these predictors are not correlated, which they clearly are, but let's just assume they're not. If we calculate the probability distribution without that correlation built in, we see these probability curves don't really line up to the data at all. And in fact, this red point is now actually fairly likely, way, way more likely under the wrong assumption than this one is. So it's very clear that, in this particular instance, this assumption is a very bad assumption. But it turns out that sometimes, in a lot of cases, you're not really harmed too badly by the inaccuracy of this probability estimate. So the reason we use this really bad assumption is that I can compute the probability, this joint probability, without looking at both dimensions. So I can calculate the probability that predictor 1 is whatever value it is on this axis. I can then separately calculate the probability of this point for predictor 2 and multiply them together to get the joint probability. I can't do that when they're correlated. And so the nice thing about this is we can very quickly calculate this probability because we can do it separately for each variable and then just multiply them together. So that's why we do it. All right, so looking at our data, the data we actually have, how would this work? So let's look at our tau predictor. That one's actually important. And so for the tau predictor, for like a numerical predictor, what we do is we typically use these things called non-parametric density estimates. So we can see for tau, the blue line here is for impaired patients, and you can see they tend to have higher tau values than the control group. So there's definitely a separation between these two groups. So there is some signal in this data. And so let's say we wanted to compute this probability. Let's say a subject walks in the door. We want to compute this conditional probability. Let's say that they have a value of 7 for their tau laboratory tests. So what we would do is we would look at where a value of 7 intersects these density curves. And we can see for here, the probability, these are relative probabilities because they're densities, but the probability of you being impaired is much higher because the curve is a lot higher at 7 than it is for the non-impaired people. So if I go over to the y-axis here, there's a huge likelihood just based on this one variable that I'm impaired compared to unimpaired. So based on the evidence we have for a tau value of 7, there's a much higher likelihood or much higher probability that we're impaired. So this is for one variable. What we would do is we would do this for every one of those numeric measurements, whether it's age or A beta or some other weird protein measurement. We would calculate these probabilities for each one of them. And for each class, we'd multiply all the impaired probabilities together to get their joint probability. Okay, so this is how it would work with numeric data, is we have like these density estimates for each class that tell us the probability for that one predictor, and then we can just read off of those density estimates when we get a new sample what the corresponding probability is. So for example, if we had a tau value of like 5, that's a situation where the likelihood of being impaired is much lower than it is for being a control. So depending on where you are in the scale, the probabilities are going to change based on where the distributions sit. So again, that's what we do for numeric data. What do we do when we have a categorical predictor like genotype? So what we would do is we would basically do like a crosstab. We would get the probability for the impaired group of being each genotype. So for example, if I'm impaired, I have the red bars here. All these red bars add up to 1. So let's say I am an E3, E4 person. So I have an E2 from one, E3 from one parent and E4 from another. So just based on that individual variable, it looks like my probability is much higher than I'm impaired versus non-impaired. And you can see if I'm E2, E2, it's actually there were no data here where the person was impaired. So you're very much protected if both of your parents gave you the E2 gene. So for a new subject that's being predicted, we would come back to this table, figure out which bucket they fall into, and then we would get their probability off of these bars. And those also get multiplied through with all the numeric probabilities that we got from each one of those distributions. So big picture, what we would do is for each predictor, whether the numeric or not numeric, individually we get their probability of being either impaired or non-impaired from the training set, and we multiply all those together to get their likelihood value, their value of the probability the predictor is given the class. So a little mathy, little bit more math that we're going to go through in just a second. One thing I wanted to say is you don't want to use dummy variables here. So what I could do is, if I'm looking at gender or sex, what I could do is I could do 0, 1, and in R, what that would assume is since that's a number, it thinks it's like a numeric data point or numeric variable, and would try to compute these densities off of binary data, which is not what you wanted to do. You would rather it generate them based on these cross tabulations than to do these really awful probability estimates by assuming they're numeric. So with naive Bayes, you definitely do not want them converted to dummy variables. You want to keep factors as factors when you give them to this model. That makes sure that these things get computed and not these really bad estimates of probabilities. All right, a lot of numbers on this page. Let's walk through it. So let's say I'm a patient, I'm E2, E3, and I have a tau value of 7. So that's what we looked at before. So if I'm impaired, or if I want to calculate the likelihood of me being impaired, what I do is I go to the impaired curve for tau equals 7. I get the value off of that. I go back to these cross tabulations, and I get my value for, what was it, E3, E3. So I go back to this, And this tells me, unlike tau, that I'm more likely to be a control. So tau is saying, oh yeah, this person's impaired. Genotype is saying, well, all things being considered, they're more likely to be a control. So what you do is you multiply those together and get this value of 0.13. Now then you do the same thing for the control curve. You go to the tau variable, you look at the control curve, you get the probability from that, go back to the cross tabulations, look at the E3 bars and get the control curve. And then when you do that, you get also a number when you multiply those two together. So what we have now is we have the likelihood of you being like the patient that you are, given whether you're impaired or not. So based on the data, like the training set, this value that I'm impaired is much, much, much higher. It's like 10-fold higher than this value. So just based on the training set data alone, I think it's much, much more likely that I'm impaired. But that doesn't factor in the prior probability. So what we have to do is we have to look at, in the wild, what the probability of me being impaired or non-impaired would be. And let's say I calculate that from the data. In the data, remember, there weren't that many impaired people there. So it was about 27% of the training set is impaired, and about 72% is not impaired. So when I multiply this number times my prior probability, from there, I'm still predicted to be impaired, but the ratio of these things is nowhere close to as high as it was when I looked at the individual likelihood data. So once we have these relative probabilities, they're supposed to add up to 1. So what we can do is we can divide each one of them by their sum, and it turns out that the probability coming out of the Bayesian model for this patient and for these two predictors is I predict that they're impaired with a probability of 77%. So what Bayesian models do, I'll answer that question in a second. What Bayesian models do is they combine the observed data in our training set with what our prior belief is. And the way they generally work is when I have a little bit of data in my training set, the prior information or my prior belief has a much larger influence on the results. So if I have like I do, like 300 data points in my training set, my prior has a lot more weight than if I had a training set of like 300,000 data points. If I had like a really, really large training set, my prior belief doesn't actually account for very much. That's just sort of the way the math works out. So it tends to rely on our non-data driven prior belief when we don't have a lot of data. And so that's just like the trade-off that you make between your data and your belief in Bayesian models. Okay, so the question is, why do you say in the wild? Do you mean literature or prior knowledge-based value? Yes, that's what I mean. That if you're like an expert on the thing we're trying to predict, I'll qualify this in just a second with a little bit of an off-color example. But you would be able to say, well, I think it's my belief that like the average person who would get predicted by this model, like which would probably be an older person, would have the probability of them just being impaired is X, just based on what I've seen in the clinic or whatnot, or based on the literature and so forth. So that's what I mean by prior belief. It's like based on, like if I was a doctor, it'd be based on patients I've seen and articles I've read and this and that. So here's a caveat though. So here's the thing is I used to work in molecular diagnostics. And so we did a lot of diagnostics for infectious diseases like tuberculosis. And if I was still there, I'm sure we'd be working on a COVID test. We worked on flu tests and things like that. Because of how diagnostic tests are reimbursed, a lot of infectious disease diagnostics are based on STDs. And so like the first set of diagnostics I ever worked on were for chlamydia and gonorrhea. And so when we go to do like clinical validation, so I would write the algorithm. So I'd be doing like this. I would be taking the observed data that we had from our clinical trials, and I'd be building like machine learning models to take the data that the instrument would collect and make predictions on what's the probability that this person has gonorrhea, let's say, right? And so then once we take those algorithms and get them finalized, we build them in software into these diagnostic instruments that you would see in a lab at a hospital, and then we take those instruments to clinical trials. And so in clinical trials, for these things, you would do a bunch of different clinical sites. So you would have like sites in cities or like in rural places in different parts of the US, like Canada and Europe and all these things. And so then when you submit data to the FDA for your diagnostic, you have to break out the performance and the statistics by each clinical site. And so the thing is, if you were to ask an expert what the prevalence would be of gonorrhea in the general public, it's pretty low, right? So it's like in the single digits. But here's the thing. When we broke it out across clinical sites, what we found is we had some sites, like these really isolated rural hospitals, that had 0 observed gonorrhea samples during the whole clinical trial. But then we had other sites that were, let's say, I'm not going to say what university, but like university STD clinics, whose gonorrhea rate was not only not 0, but much higher than I maybe would have predicted it to be. So, in our data, we had to measure the performance of these diagnostics by also doing it with the prevalence. So we'd have to answer that one question I mentioned earlier, that what's the probability that if your diagnostic says somebody has gonorrhea, that they actually have it. And so, the video just went out, but I'll keep recording. So the point I'm trying to make is prior belief sometimes depends on context. So if you were somebody who is in one of these small rural hospitals, your belief of what the gonorrhea rate is would be very different than somebody who is at like a big university clinic. So even though like our prior is based on our prior belief, that's not maybe as clear cut as we might think it is sometimes. Okay. So what's good and bad about this model? It can be very quickly trained and can be done in parallel because we treat all the predictors independently of each other. Once it's trained, it's really like a lookup table. So you can put it in a database and get ultra fast naive Bayes predictions. And if you have numeric data, it can generate like nonlinear class boundaries. So that's all pluses. The bad news is if your class boundaries are actually linear, it doesn't work very well. So with like simple data sets, sometimes it doesn't do so well. And something else that I'll say is when you have many predictors relative to the number of data points in your training set, these joint probability values that we spend all this time estimating can have really weird distributions. So let me show you what I mean. So what I did is I simulated some data where I had 500 data points, and these data points are non-informative. So the accuracy of this model should be like 0.5. And I generated 450 predictors. So what I did is I randomly selected, they're all non-informative predictors, but I randomly selected 10 predictors and kept adding predictors to look to see what the distribution of the probabilities would be from the naive Bayes model. So here's like it's a weird little animation, but it jumps around at the start. But you can see as the number of predictors gets closer and closer to the number of data points, we get these weird U-shaped distributions where the model is making very emphatic predictions even when it's wrong. So when the number of predictors gets closer and closer to the number of data points, our model tends to predict everything to be like 100% certainty of either class, even though it might be wrong. So the downside is when we have a lot of predictors and not that much data, our model tends to say one or the other class is like 100%, even though its overall performance might be very bad. So it might make some sense to do some feature selection before using the naive Bayes model. Question is, What happens when you have a prior probability that's extremely poorly defined, such as a uniform prior, or just another model altogether? Um, um, so the question is, yeah, so if you don't know much, you can do like a non-informative prior. So you can say like 50% for a two-class problem. I don't think that's a great idea. I think that 50% is, you probably could do something better than 50%, but you don't, it doesn't have to be incredibly precise. You can do, you don't might not know if it's 5% or 10%, but you could just make a ballpark estimate for what it is. So that would be my answer. So let's see. I think they're trying to reset up the event. Okay, I think we're back in. I've been recording this when you guys got dropped out, so when we post a recording, it'll have the missing 5 or 10 minutes. I'll probably only need like another 20 minutes, maybe not even that long to finish the slides, and then we can do like another 10 minutes or so of questions. Could you please let the dog out?
But it's 5:30. Let's go, Puppo.
Shh. Dog is forcibly being evicted from the room. Or not. You want to go outside?
Want to go out for a 4-7?
All right, go ahead, leave her be then. All right, so how do we do this in R, fit this model? The point I was just making, for those of you to just jump back in, is that one problem with naive Bayes models is that as the number of predictors gets closer and closer to the number of data points, the likelihood values, the one thing I just said we spend a lot of time computing, they become very like pathological. So here's a little animation that as the number of predictors approaches the number of data points, all the probabilities go to either 0 or 1. So what happens is when you have a lot of predictors, that likelihood is either 1 or 0. So even if you don't predict a sample correctly, it'll tell you I'm 100% right that this is the class, even though it's wrong. So it's like becomes incredibly definitive even when it's wrong. So here's what we'll do: is we'll use a naive Bayes function. It's in a side package called discrim. So when you load the discrim package, it enables a few more parsnip models. What we're gonna do is we're gonna optimize the smoothness. I'll show you what that means of the model. This is basically how smooth those density estimates are. Okay, good, you can hear me. So what we'll do is we'll smooth how those density estimates look. I'll show you the effect of that in a minute. That's the model-based parameter that we're going to optimize. The other thing we're going to do is we're going to create a recipe, and the recipe is going to do two things. The first thing is I mentioned that whether you're male or not is already in the training set, but it's encoded as 0 and 1. But I also mentioned that we would rather have that be a factor variable so we get the right sort of probability estimates. And so since we sort of planned for this originally when we made recipes, there's actually a recipe step called binary to factor. So when I give it a binary variable, it will automatically convert that to a 2-level factor. So that'll make sure that the probabilities related to sex are computed correctly. And then the last thing we'll do in the recipe is we'll tune over a correlation filter. So this was asked earlier about trees. what we're going to do is we're going to take all the predictors, and over a threshold, we're going to eliminate predictors that are highly correlated with one another. So if I have like a threshold of 0.5, what it's going to do is it's going to eliminate some predictors so that the overall absolute pairwise correlations are less than that threshold. So if I say a threshold of 0.5, it might get rid of like 15 predictors, but none of the other predictors that it retains will have correlations with each other above 0.5. So that is potentially helpful here. So we have two things that we're going to optimize over. I'll show you what smoothness is in a little bit. Threshold is between 0 and 1. So I'll make a grid here and do a regular grid. The threshold is going to go between 0 and 0.9 and use 10 values there. And then smoothness is going to be 1, 2, or 3, and I'll explain what that looks like in just a second. And this is pretty standard. We're just adding the model and the recipe to a workflow that we can then optimize. So let's talk about smoothness for a minute. So I mentioned we use this thing called a non-parametric density function to estimate these distributions. So you can control how those are computed. So for example, the default smoothness has a way to estimate what it thinks those density estimates should be. So what happens is it's almost like a moving average density estimate. So the values that are computed on this side only use a certain number of data points that are on that side of the distribution. So I can widen that window or shorten that window. And so the default is usually pretty good. It's a pretty smooth, estimate of what that distribution looks like. I put a rug plot here so you can see where the actual values are. If I increase the smoothing value, what it does is it widens the window. So if I use a smoothness of 3, the window is 3 times larger than it should be, and that makes it look much more Gaussian, much more normal distribution. In some ways that's good, but the problem is it's maybe averaging more data to compute this curve than it should. We don't know because the model might want that or it might not want that. So the risk we're running by doing this is by over smoothing the data, we might be underfitting a little bit. This is not necessarily as responsive as we might need it to be. So again, larger values create smoother density estimates. Now conversely, like really low values make the window really, really tight to the point where in some portions of this distribution, it might only be using 3 or 4 data points to compute the density. So you can see what it does is it becomes way more responsive to individual data points than the other values of smoothness. If you had a lot of data, this might be a really good thing because it allows you a lot of specificity and detail when you compute these likelihood values. But for a data set like ours, maybe not so much. We might be really over-interpreting data. So for example, I think there's 4 data points on this side of the distribution for impaired patients. So this region of the density is only probably based on 4 different data points. So this might be really, really over smoothing the data or under smoothing the data. But it's something we can optimize and see if it matters. And that's why we include it as a tuning parameter. So we're not going to do this much smoothing. Our values go between 1, which is the default, and 3. So it's a smoothing amount here somewhere between these distributions and these distributions. So that's what we'll be optimizing on. It's grid search again. You've seen this before. We find a regular grid. When you turn it loose, it runs fairly fast. And the results we get, if we do the show best, is it kind of like the smoothness of 2, a fairly low threshold. It doesn't allow any pairwise correlations in the predictors to be greater than 0.4. And this is what it optimized on. Performance isn't estimated to be that much better than CART. So this may have been a wash altogether. But let's look at the auto plot and see what it looks like. One thing about this model is when you run it, you'll get some warnings that say numerical probability for all classes with numerical 0 probability for all classes with observation 10 or 1 or whatever it is. It's not really a good warning message, and you can generally disregard it. What it's doing is it's computing these densities, and it has a threshold that says if those values aren't above the threshold, I should issue a warning. The problem is if I have a ton of data, or if I have really precise data, this density value is arbitrary, and it can just artificially get below that threshold for reporting that warning. So long story short, if you see this warning, you don't need to worry about it. I've kind of asked them to eliminate it, but I think they've been keeping it. All right. So tuning, autoplot. If we look at the difference in the kernel smoothness, it kind of like 2, but there's a lot of overlap in these values. So, maybe that's a real effect, maybe not. You can see why it chose 2 because the highest point here is 2. But man, it really did want a correlation filter. So if you make it 0.9, I think it's underfitting because you have too few predictors, and then it finds just the right amount of filtering, and then as you get lower and lower, it doesn't do well. So the smoothness maybe didn't matter so much, but this correlation threshold really did make a big difference. And so you can see why it picked the values that it did. So unfortunately, when compared to CART, it's about the same. Its RC curve overlaps quite a bit, and it doesn't really even come close to what the boosted tree gave us. So it was worth a try. It would have been nice if this model worked. But it turns out that it didn't really offer us much in performance. So any questions about that that we had? Okay, I'll keep going. There's just a few more slides. So let's finalize on the XGBoost model. We've already fit it to the entire training set, which is nice. And so we can take the test set, generate the probability predictions, combine them with the original data outcomes, and also get the class predictions. So that's what this series of dplyr steps do. Just to remind you, remember the predict method always returns a data frame. So that's why we can call bind these. So that's what we get. If we compute the test set RC value, it actually comes in low compared to the training set. It doesn't disturb me too much. I think it's, the amount of data here is not very large. I forget, I think it's like 30 data points. And if I compare that to like 30 resamples, I feel like the resampling estimate is probably a little bit better. But anyway, it is what it is. If I get the confusion matrix for the test set, most of the controls were predicted controls. So with the default 0.5 cutoff, my specificity is pretty good. My sensitivity if you just look at this, my sensitivity is not all that great. In fact, it's less than 50%. And you can see from the RC curve itself, the default 0.5 cutoff is here. Now, it depends on how we would use this model. If we wanted to make an equal trade-off between sensitivity and specificity, we probably would have wanted to pick a cutoff that was closer here, which would give us, a sensitivity about maybe 76% and a false positive rate of about 20%. So, I'm not too worried about this because it's not based on much data, and we already knew that our default cutoff is maybe not where we want it to be. So if this were a screening test, we might want to jack up the sensitivity if there were a treatment for these Alzheimer's patients. So, if there were a treatment, the general belief based on the biology we've seen so far is you want to catch it as fast and as early as you can. And so in this particular case, we might rather have our cutoff on this side of the RC curve because we would rather say, hey, you need to go in for further testing for cognition and perhaps treatment and get it early. What we'd hate to do is have somebody who truly has Alzheimer's don't detect it, and they go longer without getting treatment. So that, when I talk about the trade-off between positive or false positives and false negatives, those are the kinds of conversations you would have if you were developing like a diagnostic test. And you would have those, for example, with FDA and medical professionals, to figure out like which type of error that you would rather accept than not accept. So, right. So yeah, so that's our test set results. It's very underwhelming, but we knew going into it, it's a small data set, and this would just give us gross estimates of performance, and that's pretty much what it did. And that is the end of the regular slides. So I guess what I can do is, for people who are still here, like take a couple minutes and any other questions you have, I'll be happy to answer them. Again, if you think of something tomorrow or the next day, you can post them in the Slack channel and I can still answer them. But I'd be happy to answer anything you have now. Once you find the cut point on the RC curve, how do you go back and change the probability? Right now, we'll change this, but right now what you would do is you would get the probability prediction, and then you would do like a mutate and change the factor. What we are doing, hopefully by the end of the year, is workflows allow you to do like pre-processing and modeling. We also want to add post-processing steps so that that if you want to actually optimize the cutoff as if it were like any other tuning parameter, enable that. Or also enable things where you could add to the workflow that you know what the cutoff should be and you would like it to be 0.7 or whatever you would like it to be, and that will automatically be built into the workflow. So we do have some post-processing things that we want to do, and that hopefully will be coming very soon. Once David gets through some things he's working on, that'll be his main priority. But right now it's a dplyr mutate once you get the class probabilities. We're currently able to build cut points during capable cross-validation and model tuning, or is that coming? So yeah, the answer to that is you will be able to do that, but just not yet. So what that would look like would be, let me show it. What will eventually look like is when you create your workflow, let me find Naive. What you would, I'll put this in the Scratch. Is to add, I don't know, I don't know what we call it, probability threshold, and you could be like 0.7, or you could say like threshold equals tune. That's the goal. It's a little more complicated to do that, but it's not impossible to do. So we want to be able to add in some post-processing steps like that. There's some stuff we might be able to do with calibration. And also for regression models, like something that Kara can do is it can threshold the predictions. So if you get like a really, really wild prediction, like a sale price less than 0, we want to be able to add numeric bounds for the numeric predictions. So that's another type of pre-processing thing. Okay, I think there's more people typing, maybe like one question or two if you're both typing at the same time. Oh, no problem. I guess this is really what you're talking about. I've used Yardstick in the past to calculate a custom model cost. The article online is very helpful, but it was pre-involved. Is there an area of the API that is being adjusted, or is this what I should expect? Well, I wouldn't say that you should expect it. So the best thing you could do would be to put in a GitHub issue in a Yardstick and say, you could say like, hey, I told Max about this in the class. I did this custom metric, and here's what it was, and it seemed kind of like a lot of work. So we definitely don't mind that feedback. There might be some things that we could streamline, or some things that we can make a little bit easier. So yardsticks are a fairly simple package. So if we need to add a little bit more complexity to make it easier, that would be totally worth doing. So I would let Davids know by putting an issue in the yardstick. Yeah, it would. Yes, it would be hard without yardstick. It might be easier in Carrot. I don't know. Yeah. So yeah, let's go ahead in there, and I would say thank you. Put an issue in the yardstick, and I'll be around virtually for the rest of the week. So I really appreciate you guys sticking in, or everybody, everybody from sticking around, and you know. I'll be talking about similar things in my talk on Saturday, so you're welcome to, of course, see that. And we'll post in the same channel when the videos are online. Thanks.
Thank you, everybody. Big virtual round of applause for Max. I'll give him a golf clap since I'm the only one else on screen. Hope everyone else is clapping for him as well. That was excellent as always. I wouldn't expect anything less from Max. So thank you very much for doing that. I know Julia had to jump off. I'm not sure if Davis is still here, but thank you very much for being a part of this. I hope everyone here really enjoyed the time here learning about tidymodels and machine learning in general. I know Max opened up my eyes to the Mars algorithm and the Cubus algorithm during these workshops. So I'm always very grateful for that. And yeah, stick around for the next 2 days. Those of you who are, I think most of you are attending the conference the next 2 days. I have a lot of fun, a lot of great talks. Max's talk will be Saturday. We purposely put him toward the end to make sure people stay to see him. What did you say?
They're not going anywhere. It's not like, you know.
Well, true, but even when we're in person, like conferences often drop off. I always put Max towards the end. It's like, he's the big draw. I want to get him there, get people to stay for him. Plus, it's more acceptable to drink by that point. And and I hope everyone just really enjoys the conference. Remember, it's all about fun. I know it's a little weird this year, but use the platform the best you can. Do the networking, do the sessions, and do the talks, and stick around for the happy hour and the comedian afterwards. And just really, really make the most of it. So with that, thank you, Max, once again, and we will see all of you tomorrow.